around 6 kilometers. And so we decided to upgrade our modeling or our data simulation in order to also ingest these higher resolution data. So considering that our model grid is around 4 kilometers, we had to do some sensitivity experiments to see which is the input of assimilating more observation in a single grid point. So we started with subsampling and we did several sensitivity experiments. But at the end, we realized that our system is capable to ingest this kind of observation, higher resolution observation, but we had to slightly increase the error associated to the satellites from 3 centimeters to 4 centimeters. So this has led, of course, to a large increase of the number of the data that we can assimilate. In terms of error, the error is maintained more or less the same, but we had a slightly improved reduction of the bias. This change has had not a huge impact on the vertical temperature and salinity scale, which is not shown here, but I can tell you that the scale is almost the same. So, when we put everything together, so updating the modeling and updating the data simulation, we redo our validation. We recompare everything for a long time period in the whole Mediterranean Sea and several sub-basins. And here you see a summary of this validation, which means that if we validate, if we compare the model with respect to in situ data, in this case temperature data, for a period of 5 years, we don't see huge change in the scale, just a small reduction of the bias at the surface. We see instead an improvement in the due to the reduction of the bias in salinity, especially up in the first 150 meters. Here we can see time series of these different layers, which is not really clearly visible, but you can see from here that the red line, which represents the new system, has a lower error. Sea surface temperature, again, we don't have huge improvement, just a reduction of the bias when comparing with satellite observation, also when we put everything together. And finally, validation of surface currents by means of empirical cumulative distribution function. We can see from here, from validation of 2 specific buoys, Tarragona and Cabo Begur, that the black line represents the observation, the red line, which is the new system, is usually closer to the observation with respect to the actual one. Finally, so every year we deliver an updated and upgraded system that usually produce skill improvement on the product that we deliver through Copernicus. This time we had improvements in terms of new runoff for the rivers, better relaxation through the sea surface temperature, assimilation of gliders, and higher resolution sea level anomaly data. Validation shows not major improvements, some improvements in the salinity, in the reduction of the salinity bias. Thank you.
Thanks a lot. We are perfect in time, so there is time for a couple of questions. Matjaž.
Yeah, hi. Thanks for all your work. We really appreciate it downstream. So I was wondering, when you included EFAS, did you compare EFAS to river gauge stations at any point, just to see what? Because we are also including EFAS as a boundary condition in our NEMO, and I haven't had the chance to validate to see what's going on.
Yeah, keep in mind that we have not so many observations, so yeah. We tried because we had the possibility to have some information from the developers of EFAS on the data that they use to calibrate the model. So those data are already somehow ingested and used to improve the results. So what we did is more a comparison for the Po River, since we have observations directly from ARPA Emilia-Romagna. And in that case, the differences are very small. We think now we have seen from this result the past, so the validation using hindcast data. But the added value from this data set, at least for the developers of Copernicus Marine Service models, is that we can have access also for the forecast data. And instead of applying a sort of persistence, now we will be able to use more realistic data also for the forecast. Yeah.
Very interesting to follow the new developments of the MFS, particularly. Follow what we already discussed, in addition to the intercomparison with the Institute data, did you try to intercompare with NOAA forecasting system, as I said, because there are some differences?
No, actually we didn't, but it is a good suggestion, thanks. No, I don't know if you...
Does your model already take into account wind as a forcing that drives the distribution of freshwater input, the spatial distribution of freshwater input?
Well, actually, what we do for the rivers is to impose the runoff as a surface boundary condition. So, in the first grid point close to the coastline, the winds are forcing all the basin, so they are all over the basin, so also over the grid points where we apply the runoff. But we apply the runoff as it is from this hydrological model output.
Thank you.
Okay, let's move to the next presentation.
Yeah, I can. Yeah, the next presentation is from Francesco Maico, and he will present his couple system on the southern European seas.
So, good morning, everybody. This presentation is basically a follow-up of the presentation I gave last year in Tangier, where I introduced this simulation system over the southern European seas. It is a simulation, basically it is a regional coupled model where two codes, NEMO for the ocean and WRF for the atmosphere, were implemented on the same computational grid with the same resolution of the Mediterranean forecasting system, basically between 3 and 4 kilometers. This is a resolution that for the atmosphere is quasi-convection permitting, so WRF can be run in non-hydrostatic mode. And also this resolution simplifies a lot the implementation of the system because we don't need any nesting with the boundary conditions, because the resolution gap is well below the suggested limits. And so our reference system is the uncoupled ocean model that in this case the fluxes at the interfaces, fluxes of heat, momentum and mass are calculated with the MFS bulk formula, that is a set of empirical formulation that takes in account the attenuation of the solar radiation, the long wave radiation and the turbulent fluxes. Whereas in decoupling, those fluxes are calculated in the atmospheric model, transferred to the ocean every 30 minutes, and then the ocean feeds back the atmosphere with sea surface temperature and ocean currents. We forecasted a two-seasonal period, winter and summer 2021, basically concatenating 6 days of forecast overlapped by 1 day, that is the time for the ocean spin-up. And several experiments were conducted, basically changing the modules of the WRF physics where those fluxes I mentioned are calculated, so the radiative scheme and the boundary layer schemes. So, first of all, for the validation of the sea surface temperature against L3S data, we see that the bias is quite spread across the basin, both in winter and in summer. But a first achievement of the coupling is a small reduction of this, of the spread of this bias across the basin. But as you can see from the lines that show the bias of the evolution per lead time of the bias, you can see that the lines, the colored lines with respect to the black line that is the reference model, introduces a warm bias that is it is okay in the summer because at the basin scale this bias is close to zero. And the reason for this warm bias, basically, you can see in the tables, turns out to be a larger input of netted flux that comes from the coupling, mostly from the radiative schemes. And this surplus of radiative heat is not compensated by a larger amount of latent heat, and this will be discussed later. So, if we introduce another statistic for determining if we are doing better or not, we move to the mean absolute error. And as you can see, winter and summer, if we make the difference with respect to the uncoupled model, the blue colors means that the absolute error of the coupled model is lower, so the difference is negative. And so we start to see an improvement of the forecast. This is particularly evident as the lead time increased to 5 days. So the blue colors in the Western Mediterranean in winter, in particular also in the Northern Adriatic. In summer, the blue colors are more intense, but also we see some red color. That means that in some areas we are not doing better than the uncoupled. So this statistic basically tells us that there is an improvement in the mean state of the ocean. So we need also another statistic to assess the improvement of the forecast. That is the correlation that basically tells us how our system is able to follow the temporal variation of the physical system. So, of course, moving from day 1 to day 5, there is, of course, a degradation of the skills because we are forecasting, and as the lead time increases, the forecast is degraded. But when you look at the difference in the last row, you can see that in reddish color, there is the coupled model has a higher correlation with respect to the uncoupled. In the Western Mediterranean in winter, and also in large part of the Western Mediterranean also in summer, and in Aegean Sea, Cretan Passage, and so on. We also validated against vertical profiles of temperature and salinity, and there is, the coupling introduces an increase of salinity at the surface. It is difficult to see, but it is what I can say. This is most likely due to the fact that there is the coupling introduces a larger amount of evaporation. The positive bias of the netted fluxes moves the bias of the temperature in winter close to zero, so this is okay. In summer, basically, the fact that the mesic layer is thinner, the bias of temperature is quite sensitive to the different schemes of the physics of warp, so basically at the input of the fluxes. So after 1 year, I can answer a question that Christian raised in Tangier about the effect of the coupling frequency. Basically, the coupling frequency affects the skills of the forecast. So as it decreases, the skills of the forecast decrease itself, but as you can see, in particular in summer, also moving to 6-hourly coupling, the skills are a little better than the uncoupled. So the reason of this is not in the change of the mean state of the ocean, because as you can see from the tables, the fluxes, the average values of the fluxes is the same, but the decrease of skills comes from a lower correlation with respect to the 30 minutes coupling. So basically, reducing the coupling frequency, the system is not so able to follow the temporal variation of the physical system. So from the atmospheric side, we just make a very brief comparison of some of the 10-meter wind speed and 2-meter temperature with some reference data set. You can see in the yellow and reddish color that over the land there is an overestimation, a general overestimation of the 10-meter wind speed. This is a known issue for WRF, but for what is our key point over the ocean, the skills are good and bias and root mean square error are quite small. Also there are differences mostly over the land for the 2-meter temperature, while over the ocean they are quite close, and this is good for the balancing of the fluxes. So last, since we were talking about extremes, we successfully simulated the development of the Medicane Llanos on the Ionian Sea in September 2020, a quite intense and destructive event. Honestly speaking, the WRF itself, without coupling, was able to develop the Medicane unless it was correctly initialized with analysis, because if we initialize with reanalysis, there was no way, even with coupling, to reproduce the Medicane. So the introduction of the coupling was, yes, effective in a better positioning and timing of the landfall of the Medicane over the Ionian Greek islands, even if there was a very small reduction of the intensity of the Medicane. Last row, very briefly, both model, couple and uncoupled, were able to give a good representation of the magnitude of the very heavy rainfall over the land of Greece. So these are the conclusions. So basically I showed the metrics, 3 different metrics for assessing the improvement of the skills of the coupled model with respect to the uncoupled. We improved the mean state of the ocean. We improved the capability of following the temporal variation of the physical system. We made an assessment of the coupling frequency influence. So basically, from 30 minutes to 1 hour, there was no difference, but we thought to maintain 30 minutes because quite tight frequency to follow the fast evolving intense events. And then starting from the consideration of the larger amount of the fluxes that we saw in the table, we would like to address a little with more detail the key point of the radiative fluxes that are quite large and introduce this bias. And probably also we would like to test to reverse the coupling strategy for the turbulent fluxes, so calculating the turbulent fluxes in the ocean with the bulk formula MFS, and then they transfer back to the atmosphere. This is my finish.
Thanks, Francesco. Questions for Francesco?
Thanks so much. Very nice to see progress in your work. Are you also planning to then couple to hydrological and maybe to the wave model in the next future?
Coupling with waves model would be nice, of course. There is, in my opinion, a problem in the computational resources because WRF is a quite heavy, let's say, computational heavy model. If we add also waves, maybe the system will become too much, too much computational requests. In the near future, we would like to address more the attention to the heat fluxes more than the waves.
One more question?
Hi, thank you for the presentation. Perhaps you mentioned this already, so forgive me, I'll just ask it again.
Go ahead.
Do you have data assimilation in the ocean or in the atmosphere?
No.
Okay.
No. No. The system.
Do you think there is a risk of a drift then?
No, because the system is reinitialized. When we concatenate the 6 days of forecast, the system is basically reinitialized every 5 days with ocean and atmosphere analysis, which have data assimilation.
Okay, I think we can move to the next one. Thank you.
So we move to the next speaker, who is Giampiero Cossarini, who will talk about 2022 late winter anomaly in the eastern Mediterranean Sea.
Good morning, everyone. Can you help me? Okay. While I'm getting this help, I would like, first of all, to acknowledge Anna Teruzzi. She's the principal investigator of this work. And also, I would like to acknowledge all the collaborators from the Mediterranean modeling system and from the Assembling Center for Ocean Color and Sea Surface Temperature that give us great help in collecting and elaborating all the data. So my talk is about how to use how we used the operational Copernicus systems for detecting anomalous phytoplankton bloom in the Eastern Mediterranean Sea. As you well know, the Eastern Mediterranean Sea is an oligotrophic basin, almost permanently stratified, and only in the area of road gyre can be spotted some high level of productivity. But what surprised us in 2022 was to see a high level of chlorophyll in April, while usually high level of chlorophyll is observed at the beginning of March. And also this high level of chlorophyll was located much south than the usual road gyre site. So we started to investigate using observations and model results and try to identify the drivers and the mechanisms of this anomalous high level of chlorophyll. So the data that we used come from the Copernicus marine modeling system. Emanuela already presented the physical part. The biochemical part is based on the biochemical flux model. There is a data assimilation of ocean color, surface chlorophyll, and the profile of chlorophyll, nitrate, and oxygen from biochemical argo. Then we use ocean color data and sea surface temperature data from the Thematic Assembling Center of Copernicus, and also atmospheric data from the NCWF Analysis and Forecasting System. So we started to show some data from observation. We have here the map of chlorophyll of the 1st of March. In brown you see the cloud cover, so this is a particularly not suitable image to spot the chlorophyll at surface because of the cloud coverage is almost present in all the map. And in the magenta you have the contour of the threshold of 0.15 microgram chlorophyll per cubic meter, which is calculated on the daily climatology of ocean color, and which highlight the area usually interested by the road gyre productivity at the beginning of March. Here we have the sequence of all the daily map from ocean color, starting from 1st of March till almost the end of March in the left panel, and in the right panel the maps from the end of March till the middle of April. And you can see on the left part dark green area, which is the usual road gyre bloom at the beginning of March. But what you can see also spot some high level of chlorophyll at the end of March. This is the map of 29th of March, with concentration of chlorophyll up to 0.5 microgram chlorophyll per cubic meter in an area that is much southern than the usual road gyre bloom area. Unfortunately, ocean color level 3 data was mostly covered by cloud cover and prevent us to use this kind of data to follow all the event. So we use model that provide a seamless evolution in time and space of biogeochemical properties. And here you have the sequence of maps provided by the Copernicus model system, biogeochemical model system, from the 25th of March till the middle of April. And you see in dark green the evolution of surface chlorophyll, highlighting the events that occurred south of Crete. We can focus on the map of 9th of April, which showed the peak of this event, which is almost 1 month in delay to the usual time for this bloom. Then we use the standard method for detecting extreme events, so comparing the evolution of 2022 with the daily climatology from ocean color. We identify the maximum difference between climatology and the value of 2022, and we use this index calculated pixel by pixel to identify an area that we identify as the area where this event occurred, which is this in the map, the orange polygon. And for this area, we compute the daily spatial averages for several atmospheric, physical, and biogeochemical ocean quantities, in order to understand which were the drivers and which were the processes that produced these anomalous events. And we fixed the 9th of April as a reference data to observe the events. So I'm going now to start showing each one of these maps, each one of these plots, where the thin line are the evolution of 2022, which we compared with the climatology, which is the thick lines and the arrow and the vertical bars that show the percentile of the climatology. So starting from the drive of these events, which is the atmospheric forcing, we use atmospheric surface temperature from NCWF to identify the occurrence of some drops of atmospheric surface temperature in January and in second and third week of March. This is the red line on the top. And these drops were associated to cold spell events of cold Arctic area coming from north, and which well documented in literature for 2022. The sea surface temperature from the satellite observation, and from the physical ocean model showed a negative anomaly for the February and March period compared to the climatology. Is the thin yellow and the blue line compared to the thick yellow line. These negative heat losses produced vertical mixing in the area interested by the bloom, with several deep mixing events occurring in February and March. We can see that on the mixer layer depth, which is the blue line in the top plot, with several value down to 400 meters for all the area. But with deep mixing was detected also in the sequence of map, and you see the location of the dark blue or dark area is south of Crete, coincident with the location of the bloom and occurring during March. Another important aspect is that this deep mixing event and decreased at the end of March with the onset of stratification, with the mixed layer depth that increased to less than 50 meters depth. This deep mixing this mixing was the driver for the fertilization of the upper and photic layer. We can see that looking at the phosphocline. Phosphocline is the depth at which the concentration of phosphorus is higher than 0.1 micromole per cubic meter. This is the yellow thin line compared to the climatology of phosphocline, and you see the rise of the phosphocline up to 100 meters and then 50 meters after the mixing event. And we go to the end of the story. We're mixing, rising the phosphocline, the content of phosphate in the 2 minutes yet, and the content of phosphate in the euphotic layer was much higher than the climatology, and this was the good condition for the start of the bloom just after the onset of stratification, which is highlighted by the vertical blue line. After the stratification, bloom started. The consume of phosphorus is highlighted by the second panel by the reduction of the phosphate concentration till almost zero, to the usual condition in surface. We have the 9th of April, the vertical green line with the peak of phytoplankton concentration, chlorophyll concentration. Then the event started to gradually extinguish because of the consume of nutrients at surface. Looking at the primary production, which is the last panel, the violet one, the value of integrated value net primary production in the area for this short period was equal to the almost one third of the annual budget of primary production, which means that it's a kind of anomaly for the ecosystem behavior. I'm skipping this slide that just said us that this was an anomalous location. We compared inside versus outside the condition. And I would like just to spend a couple of words for the conclusions. To say that forecasting, analysis and forecasting model system, operational systems, can be a very useful tool to detect anomalous events occurring in area or time where or when the observation coverage is low. Unfortunately, as shown by the map, there was no any Argo or biogeochemical Argo float crossing the area. So we should trust the model in the sense that the model can provide a coherent analysis in a current way of all the sequence of processes that started from a cold spell in the atmosphere that drove a vertical mixing, causing fertilization of the upper layer with onset of phytoplankton bloom at the time of stratification. This event has been described by Anna in a paper which is published in the Ocean State Report, which is a product of Copernicus, which was published in the State of the Planet journal just a few days ago. So there you will have much more details. Thank you.
Thanks a lot, Giampiero, for your very nice presentation. Many questions, maybe two.
Very interesting your results, but I have a concern about the initial data from the satellite, because this production means that you have huge amount of phosphorus being in the upper layer. This is one. And secondly, the area that it is identified with the satellites and with the UR models, there is the Ierapetra anticyclonic eddy. So the only if you have in the Rotogyre indeed a deep mixing from 2000, so how much of these nutrients they reach the surface, and then the current they just transfer them in the Ierapetra, and then they just merge at 200 meters. So it's okay. The result is there. The publication is there, but I used to work for many years there. I would participate in the Cyclops experiment in the south of Cyprus. We have infused 17 tons of diluted phosphorus, and we never got any production because the environment is starved, so it was eaten by the bacteria. So this is interesting, but also I want to see some images of the circulation, because it's not make sense. Thank you.
Thank you. If I can just reply. Surprises. It was a surprise also for us to see this high level of chlorophyll, but somehow I would like just to go back to two clues about the event. The first one is the ocean color, which is data that show with the high level of chlorophyll much southern than the usual Rotogyre. And the second clue is that event of deep mixing, which is spotted by the mixer layer depth simulated by the model, is centered in the area of the bloom that we identify as the area of the bloom. Unfortunately, no Argo floater are present in the area or other in situ observation. We try to find any available information, any observation for that area to. Yeah.
It's more concerned. Just to this, exactly what I asked here to the mixed layer depth. We know that the Cretan Sea in that area is the dense water formation, but no one said deep water formation, but it's intermediate water formation, okay? And because never reached the bottom, so we don't consider that a very deep water formation. And the second thing is that my concern is you have a clearly event that something happened in the atmosphere that to get to trigger the mixed layer depth. I don't see here any analysis of sort of heat fluxes in the way to the surface to trigger the mixing. Yeah, because this is something we have studied, and we have two papers comparing the Southern Adriatic, the Northwest, and the Cretan Sea. And this is one of the main driving factors for get this mixing and for the bloom.
Okay, thanks for the question. I will ask the help from home. No, I'm joking. The analysis about the heat fluxes have been done by colleagues from CMCC, from the physical model, and also they compute the amount of deep water dense water formation in the area. And apparently, during spring 2022, event of deep water formation occurred in unusual area because of these cold spell events. It would be nice to follow which is the consequence if, first, if this event is real, and since model has to be validated. But if it's real, it should be nice to, or interesting to follow this event and this deep water and the fate of this water in the coming period.
Thank you for the nice presentation. Actually, I'm very happy that you are able to detect with a satellite at the beginning and then trigger all the research with the modeling, because you have the surface expression and then you could look about. Have you considered previous years that you might not have the surface expression from the satellite to see if you have increase of the productivity subsurface, because maybe you have eddies that can bring nutrients to the upper layer, but you don't have the surface expression of that?
Well, the last panel, very quickly, then maybe we can discuss during coffee break. The last panel is the comparison of the event of 2002 with the climatology of primary production in the area for the integrated primary production, which means 0 to 100 meter that we consider the standard euphotic layer. It was unusual, at least for how the model simulated it.
Thanks, Giampiero. So we move to the next presentation, which is from Matthias Lieser, and he's going to present his forecasting system from the Slovenian Environment Agency. He should be here. Oops. No.
Maybe we can try with the PDF.
No, sorry. I did something wrong.
Hi, thanks for organizing this conference. It was a very pleasurable few days. Yeah, so I actually changed the talk a bit. I wanted to talk more at the beginning about the operational framework that we are developing at the Slovenian Environment Agency. But now I will just briefly present this, and then I would like to say a few words about what we are doing now with deep learning algorithms. So I will be talking a bit more about current research, not so much about the operational environment. But we can start, I'll start by saying that Anja Fetih and myself are responsible for operational ocean modeling at Slovenian Environment Agency. We are running a wave model, a general circulation model, a storm surge ensemble, and a Lagrangian model operationally, and I'll be talking a bit about them. And then we are running a number of deep learning applications, and this is what I would like to discuss a bit more. So as you can see, we have a wave model, a WAM. On the left panel you can see the entire domain. We extended it down to Africa to get the southerly events through the Otranto Strait, and it's run in the Adriatic and Central Med domain on 1.6 kilometer resolution, and it's coupled to Aladdin 4 kilometer winds in the Adriatic, and then in the Central Med it's coupled to ECMWF, so it's a hybrid wind field, and it's being run daily. So if I go to circulation modeling, we are using the latest version of NEMO, also on the Adriatic domain. We are coupling it to WAM because the latest version is very convenient for coupling, so it's a one-way coupling currently. But we get wave information, we get Stokes drift inside, we get Coriolis-Stokes forcing, and we also get the additional bottom stress from the waves. For river discharges, our NEMO uses 42 rivers. We are using persistence, a combination of persistence values, so we take a daily value and we use it for a daily average and we use it for the next day, where a river gauge is available, which is not very often. And for other sources, other river gauges, we use IFAS or we use climatologies. So it's a combination of things. Again, we use we run a daily run every night. It happens, and this is the general circulation modeling part. Now, once we have the atmospheric model, the wave model, and the ocean model, we can run a Lagrangian model. There was an accident in 2018 which ended with a search and rescue. And this led me ultimately to believe that we need to implement a Lagrangian model for search and rescue operations, and we are using OpenDrift to do this. And it's quite interesting to me that I'm contacted a few times a year with a forensic task to actually try to estimate where if they find a dead body, and it happens more often than you may think than I thought, to estimate where it would be coming from. So this is now currently the main use of this framework. Okay, and then we have a storm surge modeling. As you know, storm surges are a problem in the Adriatic, specifically in the north. So we have Venice and the Aqua Alta, but Slovene coast is exposed too. And there are generally two approaches. So either you use a general circulation model, or you can use deep learning algorithms. If you use general circulation approach, that's fine, but it tends to be very expensive. If you want to run an ensemble, let's say, to get a probabilistic envelope of sea levels, this can mean hundreds of CPU hours. And it can be prohibitively expensive to run it, let's say, several times a day. So we were trying to find a cheaper way, a numerically cheaper way to do storm surge modeling, ensemble modeling specifically, and we started to develop deep learning algorithms already some 10 years ago. And this led to a series of research and a series of papers of the so-called Hydra models. And I would like to talk a bit about Hydra. So on the right-hand side, you can see a Hydra 2 ensemble for a specific event. But the key point that I would like to make is that Hydra is presenting forecast for sea level for one point, and it's running on GPUs. And this means that it's 1,000,000 times faster for the prediction that we want. So it doesn't give us the full 3D field of currents, salinities, temperatures, and so on. So it gives us one thing that we want it to give us, and this is very fast then. So, and it has a lower error than the NEMO forecast. And that said, I would like to stress that NEMO or ocean models typically get bad reputation in terms of performance, but a lot of their performance errors stems from misrepresentation of the atmosphere. So actually, we shouldn't be just saying that NEMO performs poorly. It means that the atmospheric conditions were not well represented. And one of the biggest events in recent history, 2019 floods, were a typical example where atmospheric situation was poorly represented in the atmosphere, and it did not reflect in the sea level because it could not reflect. Okay, so I'm very happy to say that our Hydra 2 is now going to be implemented within the ECMWF On-Demand Extremes Digital Twin Toolbox. We are testing this in the Baltic Basin in Estonia with our colleagues from Taltech, and you will be able to find out more details in the preprint, which will be submitted any day now. But it turns out that Hydra 2 is outperforming also the Baltic version of NEMO and their downscaling version of Estonian coast. So it's let's say it generalizes well also to other basins, not only the Adriatic. And then we are also, this is the thing that I'm very excited about, so the next generation of Hydra models is addressing a particular problem. And the problem for, let's say, Hydra 2 model, the older version, is that we feed it the atmospheric model input, but we also feed it the tide gauge input, let's say for copper, for our tide gauge. But the thing is, when we don't have data in copper, we cannot produce the prediction, because the deep learning model needs to have this input. What we did now is we extended the network to be able to ingest data from other stations in the basin, and it can learn what the sea levels in copper will be from sea levels in Venice, from sea levels in Bakar, so from Croatia and Italy. And it can provide a forecast even if we have sensor failure at our location. And what you can see on the bottom plots, let's say, is SSH in Venice and in Neretva, so yeah, in Neretva and in Venice, yeah. And so we've been hiding parts of data to see how it reproduces, so we were simulating sensor failures. And you can see on the top the Nemo version, which provides the forecast. In the middle, you can see the Hydra 2 version, which fails to produce the forecast because it doesn't have the input data. But Hydra 3 can produce reliable forecasts by inferring data from other stations. So it can still produce data even if you have a sensor failure. And it's very fast to train. I was really surprised. It's 10 times faster to train. Let's say Hydra 2 needs about 10 years of training data before it converges to where performance saturates, after 10 years. Hydra 3 takes the data from other stations and the performance saturates after 1 year. And it's better than Hydra 2. So we need 1 year of data from the entire Adriatic basin to be able to give better predictions than Hydra 2 after 10 years of training. And Hydra 2 is performing better than our Nemo. So this is it's very, on one hand I'm happy, on the other hand as an ocean modeler I'm frustrated that, you know, I think, you know, physics should have a better performance, you know, but it doesn't. So we are also, this is the general data flow of Hydra. You can see we have geophysical variables from an atmospheric model, and then we have tides and SSH. They're encoded separately, and they can then produce the SSH regression. But this is, so perhaps this is not as informative. We can talk about this in the coffee break. I would also say that, of course, ARSO is the provider for the Slovene tide gauge, so we will only be providing data for copper, even though all the predictions for around the basin are available, but it's open source, so feel free to try it out. We are currently testing it on Danish Meteorological Institute data on the Danish network. And then Hydra D, this is something that's also really exciting, but I'm not sure the movie will work. I want it to work very much. What we are doing now, no, okay, just take my word for it. We are now taking tide gauges from Adriatic Basin, a couple of tide gauges, and then we are creating a deep learning dense prediction for the entire SSH, the two-dimensional surface of sea levels, and it looks very good. So we are currently checking what the performance is of the tidal constituents. We are benchmarking it on sea level data from the altimetry, and for now it's really good. So very good performance. So we are taking point data and we are reconstructing two-dimensional surface in the entire basin, and the results are good. So just quickly, this is a deep learning wave climate emulation. It's been published this year. You can see it has a very good performance, but I'll just, in the interest of time, skip this. And our latest interest is L3 satellite data, deep learning reconstruction. This was triggered by a series of papers by a collaboration with Alex Barth and Aida Alvera from Jean-Marie Becker's group at University of Liège. And the problem is, if you have satellite SWATs, how do you reconstruct the rest? This is the problem. And we created transformer architecture. It's a visual image transformer which encodes the sparse data, the gappy data from the L3, and it creates a transformer coarse reconstruction and then iteratively corrects it, iteratively refines it to get very good performance. And the advantage here is, the advantage of this particular transformer architecture is that if you take a look at, let's say, interpolation or climatology or DNOF or also DINCA-E, the previous reconstruction algorithms, they tend to over-smooth the interpolation, which means that you won't get filaments or fronts you won't be able to reproduce gradients in the field, in the actual field. And it seems that this network is able to do it. Okay, thank you.
Thanks a lot, Matthias. Very interesting. So I think that there will be questions for Matthias.
Thank you very much, Majad. Sorry I arrived a little bit late to your presentation, but as you know, I am very interested in all your new developments based on tide gauges. I have a question I probably missed at the beginning. It seems the last one, the Hydra D, you are even exploring the possibility of forecasting where you don't have a tide gauge. But I don't know if with Hydra 3, you only provide forecasts for the points with a tide gauge, or you are able to generate a forecast for other points. Yeah. So what's the number of stations you need to provide a forecast?
So let's put it like this. Hydra 2 is a single station prediction. Hydra 3 is a multiple location prediction, but on the tide gauge's
on
location.
On the tide gauge sites,
okay? Yeah.
That's what I understood.
Yeah.
Okay.
Hydra D takes the same tide gauges as Hydra 3,
and
but
provides
it
the map.
creates the map.
Yes, but can you provide a detailed sea level forecast in a specific point without a tide gauge in the coast? Are you thinking of that? With the new...
Yeah, with Hydra D, yes.
Okay.
Yeah. We are testing. So the inputs are the tide gauges and the atmospheric model,
yes.
But the loss function is actually the altimetry. So we are actually training the model to correlate the inputs from the atmospheric model and from the existing tide gauges to nail the SLA. So this is the way. And you can, of course, from Hydra D, you can get predictions for any point.
That's the point.
Yeah.
That I imagine, but I was not sure if you have. Okay, thank you very much. Sure. Very good work.
Thank you. We have time maybe for a very quick question.
You just mentioned on this Hydra D that you are matching the altimeter. I mean, I see the big potential of the new SWOT altimeter for doing that, because you will have a much larger coverage and detailed data probably than what you have now.
Yeah. I was very interested in also in what Baptiste was showing yesterday, because it seems that we will be able to retrain Hydra D on a new amount, on a new set of data. So I'm very much looking forward to this. Yeah. Can you see this? Yeah, I would like you to see the video, but maybe in the coffee break.
Okay, yeah.
Thank you.
Okay.
So we move to the next speaker. I don't see. Oh, here he is. So Jorge Juan will talk about impact of Cumulus parametrization in simulation of cold drop event. So 12 minutes.
Good morning, all. My name is Jorge, and I'm currently working here in the Spanish Institute of Oceanography in the research group of plankton ecology and environmental challenges. But today, I'm not to talk about biochemical models or marine ecology, and instead of that, I'm going to talk about the sister of oceanography, that is meteorology, and one of the extreme events that are happening more frequently in the Western Basin in a meteorology context that are cold drop events. And first of all, introducing this type of extreme events. For those that are more familiarized with meteorology terms, these events are produced by cut off from the northern atmospheric circulation that happen in Europe, and this produce these cold air pockets that are isolated descending to the Mediterranean Sea, and around this depression, a stationary sea flux is produced around this depression. So warmer and moisture air mass is produced by the evaporation of these, in some warmer seasons, produce the advection in this cyclonic fluid circulation, that when these color pockets are stationary in coastal zones by the effect of the forcing of orography, and lifted up, reaching these color masses and producing high vertical condensation and torrential rainfall that made a lot of economic losses in some areas of the Mediterranean. The event that we want to show you here is from September 2019, and we made a simulation because, as this session is about, we have numerical weather prediction to forecast and know the risk that we got with this more frequently extreme event that happen with climate change, and in particular here with global warming. So the model that I use and my team used was the weather research forecasting model that is one of them widely used by scientific community, and I saw in other talks that was yesterday and I think today too, is also a complement for some oceanographic or biochemical models. So in particular, in our aspect there is regarding convection and high condensation events, when we have heavy rainfalls, we have to focus on how these models resolve convection. And as other parameters have in models, we can resolve explicitly or implicitly. Implicit is when you use a horizontal resolution enough higher now, where these processes are well represented. But when you are talking about lower resolution models where these convection processes needs a finer scale to be represented, it's better to use a parametrization. And in paraconvection, they are called Cumulus parametrization, and we have two different main types. The more simple schemes that we have are called adjustment schemes that are based on observed profiles of the air column. And one of the most famous and used scheme is the BMJ scheme. And with these observed profiles, the model can resolve the instability produced during these convection events. And the other more complex parametrizations that we have are the mass flux schemes. In this kind of parametrizations, all the processes involving convection and resolve. Updraft of these warmer and moister air masses, the training and training involving cloud formation, and other processes. Two of the most used schemes of this type are the GF and KF, and the difference between them is regarding how is the trigger mechanism in the model. So, for example, GF scheme gives more priority to the content of moist that have their air mass that is lifted up, and the KF model prioritizes the vertical velocity which this parcel of air is lifted up. So the model setup that we used was two nested grids of 9 and 3 horizontal resolution with 45 vertical levels. The period of time was 72 hours, corresponding to the 3 days of the event, from the 11th to 14th September 2019, with earlier steps and the inputs, as other speaker has used the RFI analysis from the European Center. Same configuration was used for the different 7 approaches, except for the conversion resolution. As we can observe, in the E0 approach, we have a control without parametrization in both domains. In the E1, E3, and E5 approaches, we use the different parametrization that I said previously in both domains, and using a recommendation from other authors, the E2, E4, and E6 only use this parametrization in the lower resolution grid. So, as I said, the objective of the work is to compare this performance in different configurations to view how predicts the precipitation amount in the region of interest where this event was produced. So in meteorology, we have a weather station instead of buoys that we use in oceanography, and is the classical method to compare our simulated data with observed one. Some statistics that we use to compare, and also to view a marine component, we also use remote sensing of the precipitation, in particular the GPM satellite constellation, to view this offshore precipitation that is not so common to analyze in this kind of studies. Now, regarding results, in this heat map that we can see in the top right of the graphic is represented the mean bias error between the different weather stations used and the configuration. And as is easy to observe, is a general underestimation, but all configuration. For example, in the last row, we represent the average values of this index, and only the configuration E1 is the one that have a positive value, so indicating that is not producing the current amount of configurations. And this configuration that is using a parameterization in both domains, in particular game fruits, is the only that can reach the correct amount produced during the 7. So, talking about the worst performance is by the parameterization, the configuration that use no parameterization in one or both domains. And talking about the station, if we focus on the last column of the heat map, we can see that the 3 more overestimated stations that are represented in this time series with the observed values in black continuous line are high overestimated now for most of the models. And the reason or the hypothesis that the author gets with this configuration is because these stations are related or more near for mountains. So the role of orography lifting up and triggering the mechanisms in this simulation is higher than the other, producing higher amount of precipitation that we got in the other stations that are more in a coastal zone, no? With no this role of orography playing a key role. Now with these Taylor diagrams, we represent 3 kinds of statistics: standard deviation, correlation coefficient, and the root mean square deviation. And in the axis, we can see the red dots corresponding to observed values. The different red dots are corresponding to the different experiments. So if the configuration dots is near from the observation, is indicating a better performance of the model. So the result that we got is most stations using a parameterization in both domains give better performance, better predicts of precipitation amount that happen in real condition. But also, when we focus in these stations that are more related to high altitude at orography, we got that the explicit resolution of convection in both domains also performs well, because this kind of configuration makes a more underestimation in results. It could be useful for this situation that the orography is playing an important role now in triggering all these convection mechanisms in these models. So depends on the station of interest or the region of our event. Here we are representing 72 hours of accumulated precipitation with the right top plot indicating the observed values by the satellite constellation, and the other the result of the simulations. So the first result that we get is most of the amount of precipitation is described offshore instead of all the models done that represent this precipitation on the continent and over important mountain range. So again, highlighting this important role of orography trigger mechanisms and consuming the stability and producing this heavy rainfall only over the continent. Other important result that is cool to mention is that the adjustment scheme, the BMJ scheme, was the most parameterization that underestimated the results. So this could be a reason, the reason that is behind these results could be that it's very specific of some regions, this kind of adjustment scheme. So in this case of a study in the Mediterranean, probably is not the best to use this kind of schemes, and instead of that, it's better to use the map fluids. And speaking about good performance, the the KF scheme in both domains was the best configuration that's performance for values above 100. So when we are talking about heavy rainfall now, that is the situation that we want to predict and forecast. So as conclusion, we got that simulation describe poorly the observed precipitation, probably because this gives all the orography is triggering as a main factor in our models, and for that reason we get as the most overestimated station these ones that are more related to mountain range. Also we got that a parameterized convection work better on our finer grids. That is the focus of this work, and agree with other authors, increasing our resolution of the model when we increase our resolution of the model, an implicit convection could make a higher estimation of precipitation in this kind of heavy rainfall. It's better to use this kind of a scheme. So instead of use an explicit resolution. And talking about inside that which parametrization is better to use or what kind of schemes, in this work, mass fluvial schemes, KF and GF, performs better than BMJ, and agree with other authors, is that this kind of soil-specific schemes make a quick consumption and stability, not producing a correct values of precipitation in other situations or regions that are not made for. So this is an example of how we can develop and enhance with the little studies the develop of models to give to society how prevent risks. And thank you for your attention. I want to thank also to institutions that supported the work, and also to Spanish Institute, the SIC and MonGOOS Association, to let me explain this work. Thank you so much.
Thank you, Jorge. We do have time for questions, so please, Francesco.
Thank you, Jorge, for your presentation. So, if I'm correct, you in the several experiments you performed, you applied the parametrization of convection also in the final grid.
Yeah.
At 3 kilometers. Okay. It's fine for the outer grid. Do you think that 3 kilometers was enough to explicitly resolve the convection? And so, can you comment the reason why you also applied the parametrization of convection on the final grid?
Okay, yeah. Constructing with bibliography, we see that the 3 kilometers is enough to view these convection processes, and is regarding to this, if we only test the convection processes only in the final grid, is because, as I said previously, it's common to use an explicit convection resolution on lower resolutions, higher than 5 kilometers, but it's not that common to use it in a finer scale. So for that reason, we want to test, because it's a problem that is called the gray zone, where we want or we should use explicit convection using parametrization. Explicit convection not using parametrization, one implicit one using the schemes. And this is a topic in meteorology and operational meteorology that is focused a lot of researchers.
Okay, and you foresee a larger amount of precipitation, am I right, on the land?
Sorry?
And with the adding the parameterization of convection, you foresee a larger amount of rainfall? Am I right? In your plots, do you see a larger amount of precipitation?
Yeah.
Okay, over the land.
Over the land, yeah, because one of the objectives of the work is to view how offshore precipitation is represented too, and with remote sensing, this is not well distributed with observed value. So,
can I, if there are other questions? No, I have a plane. Sorry. A second question. Over the ocean, there is an underestimation of precipitation, I see. Okay. So the question is about the lower boundary condition of WRF, of the sea surface temperature you used. What did you use? A slab ocean, or so with a fixed SST, or evolving SST?
I think it's evolving with the input, with the ERA5 reanalysis, but
okay. So
it's
it
running,
is okay.
Only was a one input, that was the 11th of September, and was running with this, but no were more inputs that at the start of the experiment.
Okay, thank you very much, Jorge. So we move to the next speaker, who is Alejandro Palladio Hernandez.
minutes, yes. So, good morning, everyone. Sorry. My name is Alejandro. I'm from CNR. I'm currently working with, continue the work of several research that were also in the CNR. One of them is Francisco Maico, that is here. Then Deborah, and I'm continuing with the modeling of the Po River Delta, and I'm looking into the summer drought of 2022 and doing some validation with 2017, which is on the part where we have data. Also, I would like to thank ARPA Emilia Romagna and Live Climax Po and the MonGOOS organization for being here this morning. So I'm talking about saltwater intrusion, which is a critical problem in the environment. So saltwater intrusion is, it happens because of two main, let's say, forces. One is natural, other one is human. On the natural forces we have the tides that are moving the salt into the system, into the river. So, for example, in this case, the fresh water that is coming out of the system, it's getting more salt from the sea. And also there is this human interaction with the river, for example, on water extraction, changes in land use, and alterations of the river flow, like creating some more plains for agriculture, and yeah, on that. And this saltwater intrusion has a bigger impact, especially in the socio-economical part. Like, for example, if you have some salinization of the soil, the agricultural land will not be the best, like to continue with growing the products. Also, ecologically, we can see that there is an imbalance between the fresh water that is coming out of the system and the salt water that is coming into the system. So it can change a lot about the ecosystem health. So to see the system that I am working on, which is the Po River Delta. So it's on the northwestern part of Italy. It's the biggest river in Italy, and it's approximately 1/3 of Italy's total size. So you can see, for example, the basin, which is approximately 74,000 square kilometers, and only the delta is approximately 400 square kilometers. So I'm showing you the bathymetry of the model that I am using. And also something important here to take into consideration when we're doing getting the saltwater intrusion calculations is that during summer it's a hot weather, hot and humid summer, and winters are mild, but they are starting to be a little bit more intense, I can say that. So also precipitation is around 700 to 1,000 millimeters over the whole year. And another important issue that we have to take into consideration is that the Po River is a low-lying delta with going from 0 to 2 meters above sea level. So it's going to be vulnerable to flooding and sea level rise. This had been studied by Deborah Bellafiore in 2021. And well, obviously, this also brings the problems with respect to the environment, which is saltwater intrusions and complex hydrology. So hydrology changes. So to study the saltwater intrusion in this system, I am using a SHIFEM model, which is a finite element method numerical model that was developed on the CNR. I am using the model in a full baroclinic approximation on a 3D triangular grid with several vertical layers. The grid is improved for forecast because the Climax Po is trying to look into creating a forecast system for the people that is doing agriculture in this area. So the grid is improved to that to run fast, and also, well, yeah, grid dimensions in the In the river branches, we have from 60 to 50 meters between the vertex of the nodes. Along the coast is from 100 to 300 meters and 2 to 2.2 kilometers in the boundaries, which is lower than we have seen in several presentations. So in order to see how the model works in the vertical, I am using for approximations, but it's mainly two. So it's the zeta with the fixed vertical layers, and zeta, and in zeta it's the first layer is the only one that is varying with the water level, and the other ones are varying, so water level is equally distributed along the other vertical layers. So for example, the first option that we're using, which is zeta star, the water level is distributed above all, on all vertical layers. On zeta hybrid and zeta hybrid with high resolution, this is only done in the first 10 layers. Also, to take into consideration for the presentation, zeta high resolution has the vertical layers of 25 centimeters, and zeta hybrid and zeta star and also zeta are half a meter layers at the top, like in the river branches. Now, also, to do the validation, well, we have measurements and we are validating the year 2017. For this, we are using data from agencies like ARPA, Emilia-Romagna, and also, well, yesterday we saw that EMODNet had also the data from this agency, which is really nice. So we have vertical profiles with measurements of temperature, salinity, oxygen, chlorophyll. And then on the lagoons, we have continuous measurements of temperature and salinity in all the lagoons. Sorry, I will go back a little bit. Yes, so you can see in this one the circles, which are yellow and red, which represents where we have the measurements from salinity and temperature. Yeah. So what I'm showing you on the left side of the presentation at the top is the distribution of 1 year of salinity in two different lagoons, one on the north and one on the south. And also, yeah, just a little bit going into validation already, is that, for example, the model is the blue line, the measure is the red line. So the model do reproduce really well these changes in the seasonal trends and also the diurnal, like everyday trends. And we also have water levels. So we have two water levels. One is in Ravenna and one is in Po di Garibaldi. I will go, sorry, a little back. So Porto Garibaldi is a little bit at the south of Venus, and Ravenna is just in the middle of the grid. So for these ones, we have made the statistical analysis, salinity, temperature, and water levels, and we found that a really good correlation in water levels, low root mean square error, and also for the daily statistics comparing salinity and temperature of the model, it's really low the root mean square error. So also we do not only look at the statistics, we also look at how the horizontal distribution around the branches of the systems are behaving. This is the image of the salinity distribution. So on the right side, you can see the map that was produced by the ARPA Emilia-Romagna, where you can see that the salinity arrived just above 10 kilometers into the southernmost part branch. And on the other side, you can see that the salinity is also, the salinity results from the model in the horizontal distribution. And you can see that it's a little bit overestimated, the salinity in those branches. So this is also because there are some considerations that were not taken into account. That is the saltwater traps, and also, for example, the water extraction. That is not considered in the model. But nevertheless, the model did a really good representation of this, and also to view the adaptive mesh the vertical adaptive mesh. So this is one of the best results we got. So it's the vertical distribution of the salinity. These are the results from the model. And I'm using this video to show you that, so you can see in the middle the water levels outside of this branch. This is the Podigoro branch. So we are looking at the branch. We can imagine, for example, if you see the depth, that this is the branch, and we can see that the salinity is coming from this side and the river is trying to push from this side. So it's like we're on the bottom and we're getting all the salinity from the sea. So also what I use in this video is an interpolation of the measurements, where you can see like the white lines that are frozen in the video. So yeah, the model do reproduce really well the saltwater intrusion into the system using these smaller vertical layers at the top. So also to mention this, for example, and also from the literature, that the salinity, the saltwater intrusion is mostly driven by the tides and the low water discharge. So also look at for example, the distance in the horizontal. So we are at 10 kilometers here, approximately, and just go into 2022. We are using this image to show you how bad it was, the drought for 2022. So this is a 40-year time series of discharge in Podigoro, in Ponte Lago Oscuro, at like 75 kilometers inland. And on the lower left side, you can see the distribution of the monthly, the monthly discharge of these 40 years, and we can see in the red dots that are at the bottom how bad it was the drought during this year. So also to mention, for the saltwater intrusion of 2022, we're using the CMEMS for salinity, currents, water levels, temperature, and also for the sea parameters for the model, and for the atmospheric we're using SERA and ERA5 because we're using the heat flux. We're also using parameters of radiation, rain, wind, obviously, dew point, and others. And well, yeah, since we haven't finished the simulations of 2022, I'm going to show you just two different parameterizations, which are the Zeta star and the Zeta hybrid with high resolution at the top. And you can see, for example, the river discharge on the top going into the sea, and how it's you can see it there. So also for this one, sorry, I'm going to go a little faster. For 2022, we have until the end of June, which is on the left side, my left side, your right side, the salinity intrusion on June. And for example, after 27 days after this map that I have from the numerical model, the saltwater intruded 40 kilometers. So as I mentioned before, if we see, for example, the length, so it's 20 kilometers. So it's the same river branch, the Podigoro, and it's going double with also half the river discharge into the system. So conclusions, we successfully reproduced the salinity trends in the system with a really nice vertical distribution of the salinity along the river branch. I mean, I only show you Podigoro, but it's also from Podi Venezia, Podi Pila, and Podi Gnocca. And also, for example, the simulations of 2022 showed that it's a really big impact on having like really lower river discharge. So it's a really bad drought. And well, yeah, also it is nice that it's being implemented water management strategies like climate exposed for this type of systems. And well, yeah, just to thank also all these institutions for letting me be here and show you our work. So thank you very much.
Thank Thanks, Alejandro. Questions? Oh, 1, 2, and 3. Quick.
Do you expect salinization this summer?
No, no. Yeah, we saw for example, yesterday from EMODNet the river discharge, and we have like several peaks of discharge along the system. So no, this summer.
Hi. I understand that you're very much interested in the saltwater intrusion. I'm very much interested in the freshwater extrusion. Right? Can you extend your model to the Croatian coast?
Yes, I mean there are some simulation. Actually, so we're using ShyFem. Well, we know, but in ISMAR they are using ShyFem for the whole Adriatic Sea. But it can be seen, for example, the extent of their freshwater plume to where you are. So yeah, it can be. I mean, it is implemented. It is one of the not for me, but for Christian Ferrari, which is here. But yeah, it's.
Yes, very quick. Thank you, Alejandro. So, if I understand correct, the Z-star, yes, the Z-star vertical configuration with the top layer at half a meter is the one that gives the best results in terms of.
No, the one that lower 25 centimeters.
Okay, the 25 one. This is also true for the salinity in the lagoons, or did you perform some checks also in the lagoons with the different vertical schemes?
Yes, for example, for the lagoons, we have the data from CTD, so it's point data. So what we did is take the daily average and do a comparison. Yes, there is a better results, but it's really low, but it's better with the CETA.
Okay. Thank you.
High resolution. No, thank you. Thank you.
Thanks again. So we move to the last presentation of this morning before the coffee break. So I invite Sara Morucci to give a talk, please.
Good morning, everybody. Thank you for this opportunity, first of all. And a special thanks to Gabriele Coccia, that is the father of the tool I'm going to present you today to assess the predictive uncertainty. This is a brief description of overview of what I'm going to talk about. First of all, the area of interest that is Venice, as obvious when we are talking about storm surges, the need to move towards a probabilistic approach in the sea level forecasting, the model conditional processor that is our reply to this need, and its application and some results. So, when we are dealing with storm surges, we always talk about Venice, the North Adriatic Sea. And ISPRA developed its own forecasting system that is an integrated forecasting system that uses also real-time data provided by our observing networks, and it is a ShyFem-based model system that runs every day with many different configurations depending on the meteorological inputs we use, provided by ECMWF for Bolam, depending on the grid's resolution and if we use or not the data assimilation. It has been developed in collaboration with CNR ISMAR of Venice, and it provides every day 96 hours forecasts. But this is not enough, because when we are dealing with storm surges, sea level forecasts, and very critical events, we do not, it is no longer sufficient to provide decision makers during a storm surge event or critical events just with deterministic forecast. But there is the need also to provide information about the probability of an event to happen in the future, in order to make decision makers more conscious about the decision they are going to take. And this is what we are trying to do in this work. So moving on. First of all, and so we have to deal with the uncertainty, because each time we are dealing with models, we are always dealing with an approximation of the truth, of the reality, and this is quite obvious. But it is less obvious the fact that we do not always take into account the uncertainty in our models. And we made a very big effort to assess the uncertainty. But before moving on, I just want to be clear and sure that we are sharing the same concept of uncertainty, because I'm quite sure that if I ask you what uncertainty is, I probably receive many different answers. For someone could be the error of the models or the spread of an ensemble of models. In our work, following the theory of Christophowitz, I'm sorry for the pronunciation, we define the uncertainty, the predictive uncertainty, as the probability of an event such as the sea level to overtop a threshold to happen in the future, conditional upon all the information that we have in the present of this future real event to happen, such as model forecasts. So what we are trying to do is to fix and to evaluate the probability, the conditional probability of sea level to happen conditional upon the model forecast. And we reply to this problem with the model conditional processor that has been developed by Gabriele Coccia and that I presented you a few years ago, and that we just updated, and these are the first time we present these preliminary results. I don't want to go deep inside technicalities and statistical tricks that have been used to develop this model, but I'll be around if someone of you would like to understand more. But it is, you have to know just few things, that it is a Bayesian theorem-based statistical processor, as obvious because we are talking about conditional probability, and what we obtain at the end is a multivariate distribution, where multi depends on is a dimension that depends on the number of models we used, the number of time steps we consider, and that's all. So, we have now this conditional processor, this is a statistical processor, and we applied it to many different cases. And these are the two different versions, the oldest one on the left and the newest one. At the first, we applied it just at two stations, Lido di Gasud and Punta della Salute, that are both of them in the North Adriatic Sea near Venice. And we used the period for the calibration 2018-2020, for the validation period 2022. And what we obtained at the end, it was just the cumulative probability of an event to happen in the future in the next 96 hours. In the new version, new updates and very important improvements have been done. The threshold remained the same, are the critical threshold, interest thresholds for us. There are 110, 130, and 130 centimeters of sea level. But we decided to use just Lido di Gasud because since 2020, fortunately, hopefully, during storm surges in Punta della Salute, that is the main station in the Venice city center, all peaks are cut during storm surges because thanks to MOSE elevation, so we cannot use anymore this time series because we have no more peaks. And the validation period was extended to 2000 up to 2022. And one more implementation was the use of the separated components, astronomical and meteorological, as I will show you the reason why in a few. And what we obtained was not only the cumulated probability of the event in the next 96 hours, but also the probability of an exceeding to happen for interval of time of 1 hour, that means the instantaneous probability of an event to overtop a threshold, and in the next 6, for 12, for 24, and so on hours. So these are the 8 different configurations we run at ISPRA for the Scheiffen model. As I said, depending on the methodology, different inputs and grid resolution. And the MCP has been calibrated for each different combinations of models we have that are available. And as you can see in the last part of this graph, we made the best configuration was the ABCAO. That means that we used all the configurations of Scheiffen, and we extended the period of the calibration up to 2022, but unfortunately, since the 2 last configuration of Scheiffen has been added just in 2019, we have such a small period of time series to calibrate the MCP. These are the first tests to evaluate the performance of the MCP, and these are the QQ plot related to the calibration period and the validation periods, and as you can see, it works very well. This was the first attempt we did with just 6 models, because we didn't have yet the last 2 configurations of Scheiffen. But what we can immediately see is that evaluating the main statistical indicators, the MCP, that are the blue lines, works better than the deterministic models for almost the time, the 96 hours of forecast. And this is what is more important, because this is referring to the validation period of 2022, and with all the 8 models we used. So it's the more complete configuration we can use for the MCP. And we can see just a few comments. We can see that also in this case, it works better than all the deterministic models, and that the bandwidth, as expected, was increasing the time steps because of the loss of accuracy also of the meteorological models that fed the storms, the MCP. Finally, we decided just to decide which of the many different configurations of MCP to use. We averaged the main indicators, statistical indicators, over the whole 96 hours. And we decided that the best configuration to use and to focus on is the one indicated in blue, ABCAO. That means nothing for you, but it means a lot for us. And this is the application to one of we applied it to different cases. As I will show you, one in which the astronomical component was higher than the meteorological one, and it prevails. And so you can see here in the top panel the expected value, and also the probability, the cumulative probability to overtop the threshold, different thresholds. While on the bottom panel you can see the probability in the next 12 hours and in each hour. So what I want to say is that here, just running to the conclusion, is that if there is a higher influence of the astronomical component, it works better than in the case in which the meteorological one prevails, because the meteorological component has a very high uncertainty related to, while the astronomical one, since it could be easily determined by the laws that governing it, has zero uncertainty. So we decided to calibrate it also separating the 2 different components and considering the astronomical as it has 0 uncertainty. And we applied it in this new configuration with the 2 separated components, so we obtained a lot of interesting results. It works better, and these are the well-known statistical indicators evaluated also in these 2 cases, and I will show you what it is important. And now I'm going to the conclusion. On the left side, you can see the the event of December 2022, in which we have the higher meteorological component prevailing with respect to the astronomical one. On the right side, the opposite. And as we can see, we have the higher is the meteorological effect, and the higher is in the uncertainty, and the MCP works less better, while the smaller is the meteorological component and the lower is the uncertainty. This is the same, but we applied it also. We made two different applications. The first one, we calibrated it on the period 2019-2021, and we validated it in 2022. In the second application, it's something like an hindcast. While in the second application, we used it, we calibrated it on the whole period, 2019-2022, and then we applied it also to these events that happened in the past, such as a reanalysis. And this is the second case, the case of a sort of reanalysis and the same application to the same events that I just showed you. And now I don't want to talk about I will skip this part, but I'm still around if you want to have more information. But just as a suggestion, these are the cases of storm surges happened during the period 2022-2024. We are talking about at least 50 events, and we applied the MCP also to this event to have such as preliminary statistics about this. And you can easily see from this picture also the period during the year in which they are concentrated. I don't want to show you everything, but just this, just because I don't want to ask you to believe me as an act of faith, but the MCP, the mean absolute error, has been calculated for the two types of Scheiffen model that are the ones that uses the ECMWF meteorological models, the one that uses the Bolam models as meteorological inputs, and the last columns, the green one, are referred to our MCP. And as you can see, the new version performs better than the last one, but don't worry about the fact that it do not perform yet better than all the other models because of two reasons. First of all, that we have a very small statistical sample because we have just 50 events, fortunately. And the second reason is that its performance depends a lot on the performance of the inputs we gave him. So it depends on the accuracy of the model forecast we gave him. So I'm here for any further information. Thank you very much.
Thank you, Sarah. We do have time for just one quick question. Is there anybody? Okay, Matthias.
Hi, yeah. Not sure. I'll try to be quicker. So, if I understood you correctly, you define uncertainty as the conditional probability of a true event happening given the data from the models. And the models that you use are oceanographic models, so basically the sea level predictions, right? Okay. So, so you were testing for periods from 22 to 24. So what comes to my mind is it would be really curious for me to see how your algorithm performs for the 2019 event, where the uncertainty... 2019 event, where the uncertainty was not in the sea levels. The uncertainty, excuse my term, was in the atmosphere. Yes. Is this a problem for your algorithm?
Absolutely, yes, because the uncertainty that I always said during the event that you are talking about, that is the 2019, the second most important event haven't happened during the history of Venice, probably followed just from 2022 events. even though thanks to Moser we will never know. Referring to that event, our models performs very well in the sense that they haven't been able to reproduce the exact value of sea level. But why I say, sorry for this trick, but why I say that it works well, that the system works well? Because it was not able to reproduce what happened in the sea because it has no, it had no correct information from the meteorological field. So it works well because it cannot reproduce an energy that there is not in the inputs field, in the input field. And this obviously reflects also in the MCP, because this is just, not just, it's a sort of a processor that uses the information you give him, and so he cannot reproduce an accuracy that there is not.
Thanks a lot. Sorry, Matthias, but you will discuss it more in the coffee break. So that's time to go upstairs. Thanks to all speakers. Manel, so about hydromorphodynamic service for coastal flood risk assessment. Please.
Thank you, thank you. Please pay attention, that presentation is very interesting. Okay, yes, my name is Manel Grifoll, and I'm going to present this talk that it's titled Using Hydromorphodynamic Services for Coastal Flooding Risk Assessment. This work has been done among a team of researchers from my lab, that's the Laboratori d'Enginyeria Marítima at the Universitat Politècnica de Catalunya. Well, the motivation of the work is to provide a system of mitigation measures against the storms in the urban beaches. Here, this is the example of the Celia storms in the Barcelona urban beaches, that also it has a high impact on the mass media, and also many of the citizens were worried because it looks like that it was the end of the world. But in any case, we were asked to provide any mitigations, any coastal flooding assessment to make decisions. The Celia storms occurs in 13-19 of March 22, and you can see here some of the pictures of the limit here in the promenade, in the right-hand side, on the top of the right-hand side. There is a sun, so it means that it's the maximum constant flooding. And also there were some sandbags, the middle of the figure, with some measures, some last-minute measures, sorry. Some last-minute measures. This is mine? No. It's my brain. I have powers. Well, in any way, the motivation is to try to develop a forecasting product for decision-making tools to mitigate impacts, or also to anticipate measures. And the variable, the physical variable that we have to take into account is the coastal flooding. How we have done this, the objectives, the operational service. First of all, we need to decide a numerical modeling suite. We decide the X-beach, that I will talk later, and also an eventual swan downscaling. Also has to be implemented with a robust or coherent input information, in particular the topobathymetry, as I will talk later also, that it's important, not only the bathymetry. And also the model must be properly validated with specific exercises. In this case, we're using bathymetry and also oriented field campaigns. So the workflow and also the operational chains, it may be suitable to provide near real time results, because the anticipations that we have, it's very short. For instance, the terms of hours, if we want to construct mitigation measures based on dunes, etc. Barcelona urban beaches, if you are familiar with the city, they are located in the shore face of the city. The accessibility is very easy, so this is a problem during the storm event. There are multiple of citizen uses, economic activities, there are restaurants, nautical activities, recreational. The estimation of the users is about 1 million of users per year. About the methods, we use the numerical each beach model. If you are familiar with this model, it's an integrated modeling system that it solves not only the wave propagation and the hydrodynamics, but also the sediment transport and the wet and dry paradigm. So it means that we can estimate from them the coastal flooding. It's useful to beach morphological changes due to storms, sea level rise, and also to evaluate how will be the response to human intervention. Also, it's an open source and large user community, and we have experience using this model in a barrier beach, in the Trabucado Barriers Beach, that is located in the Ebro Delta, that when there are strong events or strong storms, used to be a breaching events that we could simulate with a numerical modeling. Well, something interesting, or something that we have to take into account, it's obviously the bathymetry and also the topography, because the response of the beach also will depend on the beach profile, the submerged and also the immersed area. Here in the picture you can see how the beach profile will be quite steep, so we need to incorporate this information into the model. How is the results of the model? Here you have an example of the Celia storms. The different color lines is the maximum flooding that we got from the model according to the first hour, 5, 10, and after 24 hours. The red line, you may see that the red line is already crossing some buildings, some restaurants, so affecting infrastructure. So in that case, the civil protection must take measures to, for instance, to close the accessibility of the beach. We also use bathymetry imaging that we got from the cameras that are mounted in the skyscrapers on the Barcelona shore face, and that were quite useful to model the maximum flooding line. Here there are 3 different comparisons from 3 different storms, from the Gloria 2020, the Celia, and also the Isaac, and the matching between the model and the bathymetry in terms of the maximum coastal flooding line. I think that it's quite decent. Anyway, we did also a specific field campaign to validate the hydrodynamics of the model. We did 2 different deployments in front of the beach at different water depths, and we got information of currents, OBS, sea level, and also the most important in our case, that is the wave information, significant wave height, period, and also direction. The model validation with the specific field campaigns in terms of significant wave heights. Here you may see the comparison of the time series in blue and purple for the different mooring stations. It's the observation, and in black it's the numerical results, and using a standard error metrics like the skill score and also the rod mean square error. The results seems quite useful to construct the operational chain and the workflow. The operational chain, it's, we start from CMEMS. The system includes the both systems, the both products that are available in the region, so that means the EV and the METC. And also we get the waves. Here there is an intermediate step that we are not using, that may be certain point controversial, that we are not doing a downscaling, because we are trying to provide, in the beta version, we are trying to provide a near real-time forecasting in case that we do a proper downscaling, so this involves a more computational time consumption. Afterwards, the X-beach, 3-day forecasting, and the operational chain, it's different than probably the models that you are more familiarized. We activate the model only when we realize that there is a significant wave height more than 2 meters per second. If the significant wave height is lower than 2 meters per second, so it's not necessary, because we expect that there won't be any kind of alert. Thinking about the end users, and after some meetings with them, they ask us that the model, that's very interesting, etc., but they ask that they need some specific tool oriented for the end users. And then we design a very simple system of alert based on 4 different colors that you can see here: green, yellow, orange, and red. And the variable that we use to define the system of alert was in function of the coastal flooding. Here in the right-hand side, you might see different situations. We broke down the beach in 2 different sections, the northern and the south, and in function of the model results, we may have a different alert system. Well, this is not only to provide a forecasting results. We did some experiences in Ebro Delta building a natural-based solutions, and we were able to build an ephemeral dunes in the Ebro Delta in the cross shore direction to see if we can create an alternative to the classical groins, breakwaters, etc. Thinking in our experience in the ephemeral dunes, also we are testing large dunes, some different configurations in the model to see how the model responds against atypical storms, for instance, the large dunes or short dunes close or near to the promenade. Well, as a final remarks, in case that in some days you are interested to build these kind of models here, for instance, in the Málaga beach, may be a good spot. So first of all, a recommendation is that it's very important a regular updating of the topobathymetric information, because if we don't do that, the model, it has a trend, and after a couple of storms, the model cannot simulate further beyond. So also that it's a coastal video imaging, we think that it's a very powerful tool. However, it must be also substituted by a proper validation with conventional devices and instrumentation. Near real-time forecasting for a quick mitigation response. Currently, we are using a very simple scheme with straightforward interpolations from the products. However, as I told you before, it's interesting discussion. Is this one useful to be included? We think that in our experiences, it's not useful because there are more uncertainty in the topobathymetric information than in the hydrodynamic side. And also, it's important to incorporate a consensual alert system for make decision. It's very good that the practitioners and users, they have the model results, but they ask us, and I think that it's understandable, they ask us something useful, and a color, 3-4 colors, we found that decision. And finally, this is also when the model is already implemented, added value for coastal management. So it's very important because with the model we can decide predominant areas of erosion, specific hazards that then we can transfer to lock down the promenade, etc. And the mitigation strategies, instead of the first figure that I show you, a sandbag with the last minute measures to protect a restaurant. So if we have the model, we can decide something before the storms impact the coast. And that's all. Thank you very much. Here you have my address.
Thanks, Manel, for the presentation. We do have time for a question. One, Carlo.
If I understood, you use speech with a movable bed configuration. Mm-hmm. So in this case, how do you reinitialize the model? You take what is produced by the last thunderstorm, or you reinitialize it?
Well, my opinion, even from a numerical point of view, you can do whatever you want. But in my opinion, the good strategy is to have a periodic tracking of the topobathymetric and to include that before the storm. Because after the storm, the model doesn't matter. It's not useful for, maybe useful for another reasons, but not for the end users. So the initialization, we are doing the initialization during the week of the storm, but afterwards we shut down the model because we expect a calm period. And then we reinitialize with a new, at least, topography. Yeah.
Yes, one short question. Maybe I missed in your presentation. Thank you very much for the presentation, in any case. And how long can you provide the forecast?
3 days. 3 days. 3 days.
3 days? But
yes.
You have to do a lot of calibration or assumptions for having this type of, you do every day 3 days forecast? Or?
Well, the problem is during the interesting events that it's a storm, you cannot do a lot of sampling with 6 meters significant wave height. You cannot get the boat, the information. So even that we don't calibrate during when the model is activated, the end users, we have realized that they want to know what happens in the next 3 hours. probably because it's their work shift, something like that. But beyond, they don't care because it's also there's uncertainty. And they say, okay, what's going to happen now? I have to close the promenade or not? What is saying the alert system and the model? So it's like a near real-time forecasting.
Okay, thank you very much.
Okay, thank you so much.
So we move to the next speaker, who is Tanya. Thank you. She will talk about the heat rehope system for the Ebro Delta.
Okay, so, well, good morning. My name is Tania Lopez, and I'm going to present the new E3 Hope service. That is a project led by Now Systems in collaboration with the Polytechnic University of Catalonia and the IRTA, the Institute of Agri-Food Research and Technology, and it aims to provide an operational monitoring and forecasting system for the Ebro Delta. So to start with a brief introduction of the pilot site, the Ebro Delta is located in the west coast of the Mediterranean Sea, and it's formed for two bays, the Fangar Bay and the Alfax Bay. It is part of an environmentally protected area that is crucial for the survival of many species, like, for example, the endangered November seals. And it is also the most productive aquaculture area along the Spanish Mediterranean coast. However, now is facing increasing pressures related overall to the decreasing of the water quality that are linked, for example, to the limited water renewal rates of the bay and the continental runoffs. That can cause, for example, disease outbreaks affecting the mollusk production. For instance, in the case of the Mediterranean mussel, when water temperature reaches 26 Celsius degrees, the population stops growing, and when it gets to the 28 Celsius degrees, the population starts to decrease. So, for example, here in this image, we are seeing the Fangar Bay. These black squares are the areas where the mussel farms are, and we are seeing during the period of 2022 the percentage of time that the water was over this mortality threshold, that was over 23% of the time. And that caused an economic loss between 1 million and 1.5 million euros. So the aim, purpose of that project is to support decision-making in the management task of aquaculture and biodiversity protection. How? By providing an operational high-resolution coastal service in the Ebro Delta and the Fangar Bay, and allowing the visualization of the E3 Hope model forecast and the metocean observations in a customizable user interface co-designed with the target end users that, in this case, is the key end users is IRTA. And with this, enhance the water quality assessment and upgrade the current management processes. So, the system is based in a coast high-resolution model application, coupling in waves and currents, and it is downscaled from the MFC solution. For the atmospheric forcing, it uses the data for the GFS, though in the next version it's going to use the harmony, and for the freshwater forcing, it uses climatologies for the river, the Ebro River, and the drainage channels that are in the Fangar Bay. In the next version, that is going to be upgraded to near real-time in situ observation. So that setup provides daily, one-day hindcast and three-day forecast for temperature, salinity, sea level, currents, and waves for two domains. One of the Ebro Delta with a resolution of 350 meters, and another one of the Fangar Bay with a resolution of 70 meters. And all this information can be visualized in the dedicated web application that is the NAWI. So the E3 Hope model was validated during the period of 2000, using the data of the period of 2022. Here, for example, we can see the performance of the model for temperature. We see surface temperature and bottom. The blue lines are the model, and the red dots are the CTD observations registered by one of the CTDs located in the inner part of the Fangar Bay. So we see that the model has a good performance for the temperature, it reproduces the oscillations that occur during the year and the increasing of temperature in the summer and the slowly decrease in autumn and then in winter. And then for the salinity, I also wanted to show during this validation period the importance of what data we are using for the freshwater inputs. Here we see that for the Fangar Bay, we have 2 drainage channels that are the main freshwater inputs that provides for that comes from the rice crops. So here in the same time series during the whole year, we see in the black dots the CTD observation, in blue the performance of the model for the surface salinity with climatologies used in this freshwater data, and in orange using observations. So we see that there is a significant benefit on using these realistic river freshwater discharges when using it as a forcing. So this setup has been operational since August 2024. Here we can see in the area of the Fangar Bay, since April of 2024 to the end of the summer, the bias between the model and the CTD's observation for sea surface temperature. So we see that the lowest bias are in the area where the mussel farms are. And if we look at the time series, we see that the performance of the model was quite similar to that of the validation period. It reproduces the increase of temperature during the summer, the oscillation that occurred, and most importantly, the events when the values of the temperature become risky. So all this data is already available in the NAUI platform. That platform is a service platform co-designed with the stakeholders, as I said, that allows a user-friendly access to both the observations. As we can see here, for example, we see some of the variables that register one of the CTDs of the bay, and also the model in a user-friendly way. For example, with the capability of the early warning system, we can see the values of here, for example, of salinity that allow us to access and see and quickly see if we are in the middle of a risky period. And also, for example, with the visualization of the statistics that can be interesting for the stakeholders. Here, for example, we can see in the Fangar Bay, this is the area where the novel penchers are located, and we see during a identified period of time, in this case this is 2022, the percentage of time that the values of the salinity are over a danger threshold. So to sum up, that's a highly customizable tool that can serve to different end users communities, and with this support actionable more actionable local coastal data and support more sustainable coastal activities and biodiversity conservation. And that's all. Thank you.
Thank you. Thank you very much. Very interesting. Can I start with a quick question? Can you explain a little bit more how you implemented in your model the freshwater input? It's a lateral boundary condition. Do you associate specific salinity and temperature to this freshwater?
Yeah, now it is used as a climatology with fixed values during the year, and it all the column water.
Okay.
And then in the next version is going to be the near real-time observations with the observations that has the IRTA.
Yeah, but do you associate also a certain value of salinity and temperature to the runoff when you apply
No,
it?
not
It's zero salinity and the temperature of...
No, I mean, I'm sorry, I don't understand.
The freshwater input is not only mass flux, but it should also usually have associated a value of salinity. I guess it's zero in your case.
No, it's the flux of the fresh water has a value, and the salinity has an associated value as well,
okay,
depending on the associated value during the climatology and then to the observation of the salinity.
Okay.
For salinity and for temperature also and the flux also.
Thank you.
For your presentation. First, my comment that you are not alone. this year we have also massive mortality of mussels in the Gulf of Taranto, in Mar Piccolo. What do you think about applicability approach to another basins?
The applicability approach?
To another, for example, applicability of your approach to Gulf of Taranto, Mar Piccolo in Italy.
I mean, it is a coastal area, so the setup of the
semi-enclosed, also semi-enclosed.
So, I mean, the setup is applicable to every pilot site that has, every coastal pilot site that can have a similar approach. I mean, it allows to customize for the specific, and that's the importance of this idea. It allows us to create an ad hoc vision of it, but it's absolutely customizable for it.
Thank you very much.
Yes. Hi, Tanya. Thank you for your presentation. Just a curiosity, you mentioned, you identified 2 thresholds for temperature that are dangerous for mussels.
Mm-hmm.
But is there, or are there any other threshold for salinity that could be dangerous for mussels? And because you show time series of temperature exceeding the threshold, but is possible also for salinity?
Yeah, for mussels, I think it's not my
it's just a
knowledge,
curiosity.
but for mussels, I think the worst variable for them is temperature, but for example, for the novel pen shelf, I think is salinity. I mean, I have in the case of novel pen shelf, as we can see here, up to 36.5, it starts to be risky for them, and up to 39.7 PCUs, it starts to decrease the population. But I mean, I'm not the expert on this field, so I'm not.
Okay. It's fine. Thank you.
Okay. Thank you very much, Tanya.
Okay. Thank you.
So we move to the third presentation for Manuel about wave climate characterization under climate change scenarios.
Okay, good morning, everybody. We are going to explain a work named Wave Climate Characterization for the Ebro Delta, Northwestern Mediterranean, for the year 170-101,000, using CMIPC's wind projection. This is a part of the master thesis of the student Tobias Houghton, directed by Marc Mestres and myself, and it's a collaboration between the Laboratory of Maritime Engineering of the Polytechnical University of Catalonia and the Barcelona Supercomputing Center. Well, what is the idea? The idea is we have a 50% of the world coastline with an important risk to be affected by by climate change. The idea is, well, we have a sea level rise, but it's important to zoom to this sea level rise the change in wave climate. And this wave climate, the change of this wave climate present a high variability in the different location. And for that, we have interest in analyze this change variability of the climate, of the wave change, of the wave climate in the Ebro Delta area. Because we have present before some example of the risk of this area with flooding and erosion in the future. But the idea to do that is to implementing a common model, common wave model, common generation and propagation model like SWAN, forcing by different general circulation model. But in this occasion, we're interested in forcing these models, this wave model, with the last CMIPC's wind projection presenting for our studies. Okay, This is the Ebro Delta. I don't explain more about the Ebro Delta because Tanya explained very good all the problem of this area. But it's important to know that we have several last scenarios of important erosion and flooding in the area. In some occasion, the Trabucador beach barrier in the south of the delta was broken and had important management problems in this delta. For all of this, our objective is to develop a wave climate projection for the Western Mediterranean Sea, for all the Western, but in particular for the Catalan coast and more concrete in the Ebro Delta. For the last 30 years of this century, and using the last disponible wind projection, the CNPCs, and under two future scenarios, the SSP2 4.5 and SSP 8.5, sorry. Okay. In order to do that, we are employing the SWAN model, and we are implementing this SWAN model with three nesting domains. The first of this domain is for all the Western Mediterranean with a resolution of 50 kilometers. Then we are nesting in this regional model intermediate model of the Balearic Sea with a resolution of 3 kilometers. And the last, the high resolution model for us is the model in front of the coast of the delta with a resolution of 1 kilometer. Okay, we configure this SWAN model with this mesh, and with all the parameters that we are proving and testing in previous work on our lab, in particular, published in Payares et al. In 2014. Okay, we have this implementation. What we need to do first a validation of this implementation in the three nesting domain. And then with this validation, we want to be sure that the model working. And then when the model is working without big errors, then we forcing the SWAN model with the generation circular model we had disponible. In this case, R20 model. This general circulation model had a historical part, and then with this historical part, we doing a ranking of the different models, comparing with the observation. And when we have ranking this different general circulation model, we use the projection in the future with this general circulation model in order to analyze the different weights climates in the Catalan and Ebro Delta zone. Okay, the first step, validation model. In order to the validation, we have using ERA 5 analysis wind data, and we ran the model for 15 years, from 1999 to 1014, and we compared the results when the data from 7 buoys distributed along the Western Mediterranean. Here you are the position of the buoys, the latitude, longitude, and the name of these buoys. And then we, doing the validation, comparing the numerical result with our observation using the classical metrics like normalized error mean square, normalized mean bias, and correlation coefficient. Okay, well, here you are the first result for this validation. This is the significant wave height from Tarragona buoy. It's the closest buoy to the Ebro Delta. For these 7 buoys, we had the result of all done. But in order to simplicity, we only show that. And these are for a short period of months, but the table at the metrics for all the period for the tres mesh, okay, for the tres domain. The A domain is the bigger domain, the Western Mediterranean domain. The B domain is the intermediate domain, the Balearic Sea domain, and the C domain is the higher resolution domain in front of the Ebro Delta. This is for significant wave height, and this is for wave period. You can say we have good correlation in both variable, significant wave height and period, but not so good for bias. Okay, we don't have a improved resolution for bias. Here you are the result for the directions. The first wave rows is from the buoy, and the rest of them are for the different mesh. And we apply the metric, in this case adapted for this kind of circular variable, and we obtain the result. Are not, for this result, are very comparable with the result publicated for weight model in the Western Mediterranean Catalan coast, and then we think are interesting in order to use in this configuration for calculate or to project the waves in the future. Okay, with this idea in mind, we force this configuration of SWAN with these three mesh with the set of 20 GCM model disponible. Some of these 20 GCM models have different resolution, of course, and we have a historical period. During this historical period of 30 years, we have a fair ranking of model, as I explained before, but this historical period for this GCM model are 1985 to 1014, but we have only 50 years of evaluation because it's the year we have observation for all the buoys and we have compared with the result of the model. And we're ranking these different 20 models using two specific metrics. For the significant height, wait period, we use the distance between indices of simulation and observation metric, is the DSOC. It's an evolution of the Taylor diagram, okay? And for the direction, the Kuiper test. We run the model, apply the metric, obtain. This is the main, the results for the daily mean for all the period of model, of the run models, okay, 50 years. And as you can see, in the black line are the observation. The red line are the evaluation model forced by ERA5, and the rest of line are the rest of the GCM models. All of them are have a important negative bias from the observation, but they reproduce very well the seasonal variation of the year. Okay, and that is the result for the direction. Only a little set or subset of this general circulation model reproduce in some way the direction. The rest don't reproduce this direction. But this subset of model, as the model has a higher resolution for winds. Okay. Well, we apply these two metrics, the DISO and the test specific for the direction, and here the order of the different general circulation model. The top 4 model are the model with a high resolution, I explained before, and with these 4 models we obtain the different wave climate projection. In particular, we are analyze the mean wave climate and the extreme wave climate. The extreme wave climate, we are calculate this extreme wave climate with the pot or peak above threshold method, with the limit of significant height and duration of the storm that are usual in this part of the Mediterranean coast, and applying a generalized Pareto distribution in order to calculate the different return of period associated with the different significant height. Here you are a resume of the result for the wave climate change. The more important conclusion of the result are the results showing reduction in significant height in the Western Mediterranean. This is the point of the buoys. The color represents the percent change with the climate, the future climate with the actual, and the blue colors are decreasing of this significant height. And this reduction is more important in the more extreme climate change scenarios, as you can see. Here you are the same, but for the stream wave climate. For the stream wave climate, the conclusion for the Catalan coast is the same. The stream weight are reducing in the future. For the two scenarios, climate change scenario, and for all the three return period we are analyzed, 1 year, 10 years, and 100 years. But it's not the same for the rest of the Western Mediterranean. For the rest of the Western Mediterranean, that is not the same, okay? In some occasion, it's increasing. Okay, the conclusion, the more important is decreasing in significant height at period weight for most model, in particular for the model, we are the top performing model for us, and decreasing in extreme significant height for the Catalan coast, but not for the rest of the Western Mediterranean. And that's all. Thank you very much.
Thanks so much. So we do have time for just one question. Is there any? Yeah.
Maybe I didn't correctly understand. The model A is the one with the lower resolution?
The A is the bigger, sorry. Yes, the A is the bigger domain, the Western Mediterranean domain, with a less resolution.
Okay.
Sorry.
And in your validation?
It's the bigger,
yeah,
extension, but the less resolution.
Yes, okay. So in the validation, it seems that the three are very similar in terms of error and so on. But in some cases, the A, seems to have a better performance with respect to the others. When you have the peaks.
Yes.
The red is the one that has.
One buoy, 2 months.
Mm-hmm.
Well, yes, maybe in this situation, but this one we have another. Well, yes, it's the bigger one, the bigger domain. In some occasions, don't have a lot of difference with the high resolution part of the model. That is okay. But this is only for 2 months, 1 week.
Mm-hmm. Okay. Thank you very much. Thank you. So now we move to the last, but of course not least, presentation. Thanks a lot for moving your presentation to the final. So we have Francisco Campuzano. I can. It's on the right. It's on the right. Muoviti in questa direzione.
Well, good morning, everyone. I don't know if it will be the format all right, because I saw that everyone has their format changes, but well. So my name is Francisco Campuzano. I come from Plus Atlantic Collab from Portugal. So the westernmost part, probably the westernmost presentation of the session. And I want to talk to you about some approach that we are doing for an area where we are applying several projects. So I will focus a lot in a project called Lancelot, but I will talk you about this kind of effort that we are doing continuously. So just to give you some overview about the location, I will be talking about the Tagus estuary and the Sado estuary. This is in the central southern part of Portugal, and it has a very wide diversity of areas because we have submarine canyons with more than 2,000 meters deep, very close to the coast, intertidal areas, rivers, and I will explain you a little bit how it works. But then we are focusing on looking on the continuum in several ways, from the salinity, so land-ocean continuum, and the continuum from permanently submerged and permanently immersed. So this kind of continuum that also exists. Just to show you a little bit the motivation of why we are doing this is an area very highly populated with 3 million people living in the area and growing. And then we have some ports. It's a very touristic area, as you all may know. We have aquaculture production, many research and knowledge centers around. And from the environmental point of view also is a very protected area. I mean, they have, each estuary is protected, but then we have marine protected areas, a natural reserve, so Ramsar, so many figures of protection. But just to give you an overview of the physics that happen here, we have the influence of the ocean water that is coming from the coast, and then we have these two main rivers, so that gives the name to the estuary, the Tagus and the Sado rivers. But then we have many other rivers that normally people, they forget about them because they're like, okay, the Tagus is the biggest one, so the others are like, yeah, we don't care too much about them. But there are something that are very big, and they can have a lot of influence. We have a small mountain range that generate shelter areas, and on the south of each of them there is a marine protected area. Then we have the boiling event that is bringing water to the surface, rich water and cold water. Tides and waves coming also from the ocean, and then we have problem with erosion, flooding, and it's a very dynamic area. We have a plume with the tides, it's going in, out, spring, nips, and then we have like aquaculture production. So it's an area with a lot of uses and a lot of variability, even if it's a small area. Then we can continue. This is like also bathing water area, so if we continue, we can put layers and layers on it. So we made a numerical model on 3D with high resolution, 280 meters, and then we are using Copernicus global that goes to a regional model for the Western Iberia, and then we add the tides from FES 2014. But then we are also using high resolution meteorological data from IPMA, there's the National Institute in Portugal, so 2.5 AROM. And then we continue with NOAA because we have the forecast, we have free access to that. And then in the river side, we have data from the Portuguese Environmental Agency that is also available through EMONNet. So this is the result. We provide this data. Everything is published in NetCDF, CF, hourly data on the surface, 3 hour for the 3D model. We distribute it through OpenDAP and Thread Data Service. So this was also funded by the Copernicus project as a coastal project. So then everyone has access to this, and we can generate a lot of services on top of this. Like this is one of the platforms that we develop in-house, and we apply for us, but also for others. But we can do also oil spill modeling or search and rescue activities online with MOIT. The model is that is running the operation is MOIT, but also the MOIT Lagrangian model, we can run it and distribute the data in different formats. And now in the new version, we can also play with the capacities that the Thread data servers allow us. So it will be easier and easier for people to develop service and obtain the data and everything. The evolution of it in the future is similar to what was presented before. So we are coupling with SWAN, we are coupling also with XBits to produce, especially in the context of Focus project, to produce this kind of flooding, compound flooding events, overtopping. So, very similar to the type of work that, we are not as far as they are yet, but we have similar problems, as you can see, this overtopping situation near the coast and near the roads. And then we've been doing validation. This is with the tides, that is just in Cascais, in the ocean side of it. Also with thermosalinometers that they are passing by the area, but it's difficult to get a lot of data in these areas. And this is one of the things I want to talk you about. We've been doing validations also for temperature in this buoy that is with this yellow circle. We compare with EBI. EBI is the orange line, and the blue line is our model, the green line is the buoy. So there is not many buoys normally located in estuarine areas. And this is for salinity. This is where we are saying also that salinity matters. We didn't compare with the MET. I don't know if the EV now is IFAS, I don't know. But the salinity in the outflow of the Tagus is very different from what we achieve compared with the buoys, that is the outermost buoys that we have salinity, with the salinity that there is in EV. So in Lancelot, this project, what we are trying to do is to combine a lot of information in this land-ocean continuum, taking remote sensing, taking in situ measurements, low-cost sensors and modeling, because we need we think that we need all this information, especially we have this gap in the coastal area. So the project is relatively big. It started this year. It's led by Deltares and it's a 4-year project, so probably I will tell you about more in the next oncoming years. And they develop what they call the Lancelot Integration Labs. One of them is the Tagus and Sado estuaries, and we will be working on marine heat waves and flooding. So we will try also with model to cover the water sets that we don't have data, but also we will try to get more data and try to get data involving the citizens. So Lancelot is land sea, and lot means let's observe together. So let's try to bring the society to monitoring. This is a courtesy also of Patrick Gorint, that you all may know, and is working a lot on this subject. And even the EU is now requiring that 20% of the data will be collected by the citizens. So there is some kind of mandate. So we are collaborating with the national agency, the environmental agency, to say, okay, where do we deploy to do this co-design? Where do we measure? And we are trying to locate, now we have a catalog of low-cost sensors or cost-effective sensors. So one of them we want to just locate beneath a bridge or something that, I mean, they cannot be vandalized easily. But we are also bringing other communities to the idea that is, especially we are focusing on aquaculture producers. And then we are using this, we will use this kind of sensors. I have one of them here. So it's like a cap of a plastic bottle. But this one can have like 15 years of hourly temperature data, okay? And it's relatively low cost. So the idea is, normally when we are talking about citizens and citizen science, we are thinking, okay, it's someone that is working in an office and then in the weekend like to stroll in the coast. And then we thought, okay, maybe we can change also the vision and try to look for the citizens that they are already there. I mean, of course that they're professional, but they're not professional in observing. They're professional on their own things. And sometimes they can have different formation or background. So these are the areas where they are already there. So the green areas are production areas. No, the orange ones are production areas, and the green areas are areas that they are expected to develop aquaculture. So we can go to other areas within the estuaries where we don't have almost any data, because we have data for the Tagus, but we don't have data for the Sado. I mean, when we go inside, it's total blackout. And then the idea is to try to help these people to provide them the data and be the kind of the godfather of the sensor and collect the data and help us. Also, we are looking on the marinas as another potential user that can help us to collect the data. Even very fancy marinas like this one, or fishermen marinas. I mean, we can collect and locate this thing. And then start looking at some of the remote sensing products to try to compare these water levels. Like, I mean, I like the presentation of the SWOT this morning. Maybe I will try to use it too. But this is like Sentinel-3 temperature. And you can see in the center that we already have some pixels inside, because a good thing is that we are in the south of Europe, so we have a lot of clear skies. And then we have to use this. And now with this resolution, and also these two estuaries they have big bays inside, so we can get some data inside. And we can compare with this low-cost sensor, we can compare with other observations. So this is the big objective and kind of the message that I wanted to bring here on how are we planning to move into this direction. So we need more data in the landscape continuum, because we have data in the ocean, data in the river, and data in the river we know that it's not that accessible sometimes. We need near real-time river data also for other small rivers, and to try to have a freshwater budget that enters the estuary, not only just the biggest river. The society can help, and we can try to engage with the stakeholders and with other users, and this cost-effective technology can help. So, and remote sensing, we will show you in the future. So, that's it. Thank you very much.
Thanks a lot. Thanks a lot, Francisco. Do we have questions? Yes, one.
How do you calculate influence of tides on oil spill beaching?
Sorry?
How do you calculate influence of tides on oil spill beaching?
How do you get the tides to the...
On oil spill beaching, on not to trajectory of oil, but to beaching of oil, to stranding of oil, to arriving all to the coast. How tides,
how do we bring the tides from outside to inside? I mean, what we do is we use this phase model, and then this phase 2000 we have the harmonic component that we put it in a larger model, and then we do downscaling from this larger model into this 280 meters. But still, when we talk also about bathymetry, sometimes you have a bathymetry that you don't know how old is it, and it's difficult even to validate if the tide. Okay, thank you.
Okay, one last question.
Thank you, Francisco. How many sensors do you expect to grant to the citizens?
I mean, in the project we are thinking on two big buying periods, and then with the first one, I mean, the idea at least is that to have at least 25 of them. This is the initial approach. I mean, it has not been already consolidated, but to have 25 distributed along the estuary. So we can see the variability of the temperature. For instance, that is a variable that is relatively easy to measure, but instead of having 1 point, try to see how it is in the intertidal area, different channels inside, and then probably to try to have 3 or 4 tidal gauges or water level, because at the end the same river and tides is just water level converting to tides or into discharge. So at least to have 3 or 4 of them.
Yeah. It's very interesting, this citizens' engagement.
Okay. Yes. Thank you. If you have more questions, we can talk.
Yeah. Thanks a lot. So with this, we close this session on the modeling, and thanks a lot again to all the speakers and for sharing your last updates on this field. And now I'll give the floor to Svetlana for the next session.
Yeah. Now time for applications, and we start. We reordered a bit our presentations. So first floor is to Igor Ruiz Ataque, CMCC, about oil spill modeling. Please, Igor.
I'm searching here for the PowerPoints. Let me see, maybe it's on discharge. I think this is it, right? Okay. So, hello everyone. It's a pleasure to be here. It's my first MonGOOS, especially in Malaga, where part of my relatives are from. So today I'll be talking about Witoy on cloud. So it's our oil spill forecasting system, simulating system as well, and how we are using Madslick 2 in the context of digital twins. So the idea is to bring this, show how we are using our systems inside these projects that are not only the project that I'll be showing, but all of the other projects developing within the European context. So I think the first question that I wanted to raise is what means the digital twin? So a lot of people are talking about digital twins, but what is the origin, the name, why it's being applicable so much lately? So according to the bibliography, the first official definition was made by NASA, so rocket science, so explaining how the connection between all the modules, sensors, and everything can be applicable on a digital system. So, of course, this is dedicated to rockets, but how we can apply that to our earth sciences scope. So I brought here just some illustration on 3 among the projects that are working with digital twins. So of course there are several others, just as Francisco was showing, and also very small scale that are building solutions between or focusing on a given context. So today I'll be working and talking about with Oil Cloud, which is within Instituto Data Lab, or the Instituto Digital Twin. So in order to deploy the solution to Instituto Data Lab, first of all, we wanted to reproduce what we do internally, or HPC systems, but on a cloud. So I think this was the first step, that how we needed to stop and think how we could change this paradigm of running local to a container-based approach. So basically, this is the overall idea on how things are really working. So instead of having the MetaOcean inputs ready to do the simulation, we download them from Copernicus and Climate Data Store from ECMWF, and we do the data pre-processing on the fly. So we download this data, transform it, and then we perform a MEDSLIC2 simulation. So that is also, I think this is the back end, but this is also being controlled on a user interface made in Python as well, Streamlit, and everything is containerized. So in the next slide, I can show that basically all of these different modules that I was explaining, they are within just a Docker container. So all the elements, libraries, Fortran, Python are within this application, and then we can support and send this container to several other places, not just Edito. So, but at the end, we reduce the complexity of installing and trying things in different machines all the time. So we have that application that is usage ready. Also, downloading data is reducing also the complexity on how to rely on different data sets. And so anyone can use it any given time, considering it has internet access. But if you're talking about Edito, a cloud system, it will already be there, it's given. The interface, the idea was to diminish the entry barrier for people to do oil spill modeling. So we want to add new stakeholders to how to really do simulations. So the focus on Edito for wheat oil was really that. So making it widespread, making it portable, and making it more usable by different people from different backgrounds, not only scientists, not only oceanographers and so on. So here I have not a live demonstration, but a video on showing how this is currently working on the cloud, and it's accessible for people who have Edito accounts, so you can launch by yourselves too. So basically, run the video and pause and explain. So this is an experimental oil spill in Taranto, and here basically I'm on the Edito framework. So I'm launching the with oil cloud, the container. So it will pull the image from the internet, and that's it. The model is ready to run. So the interface, this is on the internet already, so it's not based on a local computer, and it's very simple user interface made with Python. So I'm an oceanographer and I made it, but it's also very interactive, so the user can navigate, select a given point. This is hypothetical, we don't have an oil spill over there, and you have information about the latitude, longitude of that oil spill, and then you can change dates, for example. So changing the dates, the backend will choose the correct data set according to the date. So either reanalysis, analysis. If it's a Mediterranean, it will suggest to use MED-C4 as system, or you can choose global. But if you're outside MED, you have to use global. And then here you put some characteristics of the oil spill, so the density, basically the volume that's going to be spilled. You can change the duration of that oil spill, so it's either continuous or instantaneous.
And here, unfortunately, you have to provide your user access to Copernicus and also to Era 5. So this is not something that we cannot simply give to any user. So they have to have their own access. And here, basically put a simulation name, and we can follow what is going on through the interface. So right now, it's telling that it's downloading this Copernicus data for that given region. So it's subsetting just the correct amount. We don't need a lot of dates. We don't need a lot of layers. So it's downloaded, processed it, and now it's downloading Era 5. Same thing done. Everything's processed. And now it's transforming that into Matzlik 2 inputs. So it does not use NetCDF directly. So we need to transform that to the ASCII files. Takes a while, but it's done. Then we do also that for bathymetry, coastline, and everything is ready, and the simulation is running. So this will be computing, so doing the equation, the advection, diffusion inside Matzlik. And when everything's ready, we can navigate to the results and do some interactive display. So we can navigate through the oil spill simulation result. So I'm just waiting here because I don't want to forward the videos in PowerPoint, but it takes, I think, less than a minute. But so that's ready, and then the user can navigate to the results and check what has happened. So this is the event that has been just simulated, and here the user can interact with this figure in HTML format, and not only interact in terms of space and zoom, but also in the time steps. So you can choose either initial, middle, or the end of the simulation. And you can do more or less the same thing. So you can check and follow, see if the currents are, where the currents are defecting that oil spill, and so on and so forth. So basically, this is the idea. The idea was to make it as simple as possible. So we have, of course, oh, something happened here. It closed the PowerPoint presentation. Let me check. Maybe I need help here. I don't know what happened. It just closed. And I... Now I just need to present again. So that was the end of the video. And for final considerations, I think this is one solution. This is not just the final. Maybe we want to do some much more development for it. And it could be deployed to other clouds. Maybe it doesn't even need a container. So those questions we will learn as we navigate through the project. And we also can ask not only in terms of technical deployment, but the integration of other circulation models. So not only the Copernicus datasets. So in fact, we already tried that with SURF outputs and Delft 3D outputs, and the system worked well with the same interface and the same pre-processing. So this is also a goal in Edito. So integrate the different work packages and not only rely on these datasets that are production ready, but you can do relocatable model and then apply oil spill modeling at the end. And the interface, of course, it could be make some advance. It's very simple, so that was goal. The goal was proving that we can do it. And in fact, I imagine that most of you know Giovanni, and yesterday he was calling me and asking for some details, some help on how to do modeling within Edito. And I was able to try to help him, and I did simulation on the phone. So now I'm running a Fortran model on the phone, so this is really exciting. So it was something that was really hard to see some months ago, and now we can do that. We can deploy, and what could be expected in the future. So a lot of questions, a lot of exciting opportunities. And that's me.
Thank you very much, Igor. Any questions from audience? Please, George.
Fantastic work, congratulations. One thing that, as you ask some, say, to improve the system, when you're running the MESLIC, it's advised just put the time, an hour.
Yes.
I mean, each time it's running because maybe the user may think that it's stuck. Is one. The secondly, you mentioned that the possibility to use other circulation model.
Yep.
I advise you to look the legacy of the MEDES 4MS project, where we have managed to set up common formats for up to 28 ocean forecasting system for the Mediterranean in order to be able to be used by 4 different oil spill models, including the MESLIC 2. So look on this. I think there's a special manual on this, how to do this. And we offer our data in this special format in order to test your system.
And that is awesome, George.
Yeah. Okay.
And just to answer the first question, so it was by default I removed the time steps because I was thinking a very non-specialist user. So if he, she is looking at time steps, what that mean? So I removed to reduce the amount of information, but maybe we can have just a click box where advanced users can also navigate through the system, because that's one thing that's missing. For example, if one wants to change oil spill parameters, horizontal diffusivity, wind age, so how to do that? So only advanced users really will be able to interact with those parameters and also see timestamps.
It's very nice. Don't run away.
Next presentation.
This is very good. I figure this can be easily applied to events like this multilagoon event that we had. It's also something that is floating on the surface, mainly wind-driven. So probably you can follow not only oil spills but also spills of multilaginous aggregates on the sea surface,
yes,
right?
Definitely.
That would be very interesting. How do we get access to that, and how can we? And is it operational at the moment?
So what I showed is basically now within Instituto, so the digital twin project, but we're also aiming to deploy the same, sort of the same solution within SAMCC framework. So that is already, we have actually a web page called wetoil.com where people can really use the system, but it's not the same one that I showed here. So it's using MESLIC at the back end, but it's a different interface and so on. So we will work on that to deploy a new version within SAMCC that will be also following the same standards. So anyone can navigate, access, do simulations. So you can simulate the phytoplankton aggregates as an oil spill. Of course, it's not the same, it's different, but you can do that. And this we plan to launch it soon, together with Agito. So we have another project, but we also have outside of it.
Thank you very much, Igor. Next presenter, please, George Zodiatis, Orion, Cyprus. And talking about mucilage, the problem is that we don't know stressor. Who is stressor? Temperature, phosphates, some pollutants. So we need to work together with you. We ask you about stressors, and after that, our people translate this to the code and run Lagrangian model. Now we don't know stressor.
Okay. So allow me to step down because I have a problem with my glasses. So it was, I thank Igor for this introduction and the new developments about the cloud possibility of running a MESLIC 2 version. In my presentation, I will show you the use of the MESLIC and the downscaled Copernicus data straightforward for coastal application of oil spill in order to get this offensive security certified professional qualification for the port of Limassol in Cyprus. This project, it was carried out in the frame of local authorities from Cyprus. The coordinator, it was a private company from Spain, Orbitaleos, if you know about, and with partnership from CMCC Bologna and from Cyprus, Orion, and the University of Nicosia. So the outlines, just I remind you about the oil spill response in real oil spill incidents in the Eastern Mediterranean the last years. The implemented scenarios for this offensive security certification, and I think it's an example how the users, the authorities, they request. Then the summary of the oil spill predictions, and we'll review 3 of the 6 scenarios very quickly. Then I will mention about the oil booms and the artificial booms. I mean, it may be of interest to you, and some conclusion about this application. So what we have, I mean, just to remind you, the last year in 2020, I don't know, it's working. We had this big oil spill incidents in Syria, from Banyan Power Plant. And 10 years ago, 15 years ago, we had the GIEC power plant in Lebanon. In both cases, we from Cyprus as well as CMCC from Italy, we have responded in operationally. We supported REMBEC, is the Regional Emergency Response Center for the Mediterranean. And we provided these daily predictions through bulletins and so on. But what was important that we have, I mean, the oil spill, it was more than 10,000 tons, 10,000 tons of crude oil. So in the present application, and this is an example, also we have used for this oil spill, the real oil spill incidents in the Mediterranean. This is a warning report, the upper top. Here is a warning report from EMSA. This is satellite data that we get it from EMSA portal, the CleanSeaNet. And this is the MESLIC predictions and a relevant, say, publication. It was published last year and with the, say, statistical evaluation. So what is this Port Offensive Security Certified Professional? When I was also requested to participate in this activity, I said, what is this? At the end of the day, is requested for us to carry out certain oil spill predictions in order to get this certification, the Limassol port, because the request, as I want to show, it was to provide the certain scenarios and to find the impact from each of the scenarios to the coastal area. It's on this is the coastal area of the Limassol Bay, because they are located the city of Limassol, located a high start of hotels like Four Seasons, several private marinas, as well the port, a fishing port, and as well as a coastal park. One of the peculiarities of this area, as you can see here, is a long line of wave breakers. I will show later why this is important. So these numbers, they just indicate the different scenarios within and without the port. So very briefly, the scenario, the description is each, one page each, but I tried here to summarize As you can see from here, I mean, also related to the coalition of different cargo fishing vessels, when, for example, they are inside the port or in the entrance or outside, when they have, for example, even a case with a transfer of fuel from one vessel to another, so an accident is going to happen. They describe how this accident was cased, but this is not our case. Our case is just how much of the oil, and as you can see, it's up to few hundreds of cubic meter of oil, or marine diesel, I mean the fuel for the ships. And of course, how long it was lasted, the release of the spill, and the locations, of course. So this is all the descriptions. We don't want to throw, and then this is the setup of the oil spill prediction. For these simulations, we have used a downscaled Psychophos data for this area, 1 kilometers from the Copernicus Mediterranean one. And this is we have used 2017-2018 data, as well as the Skyron wind. So all this is the requested scenarios, is quantities, as you can see, is very insignificant, but for them is significant. For us, it's very small. And if it is instantaneous release, how many hours? I mean, up to 8 hours. And the season, they wanted winter period and summer. So we have run for these 2 years up to 96 scenarios, oil spill scenarios. For these 2 seasons, it was for winter, it was December, January, February, while for summer it was June, July, and I think even September. So just to get an overview of the winter, say, what is the prevalent winter in the area. This is the Skyron winds. The top is refers to the winter. As you can see, there's more variable. We had the southwesterly and as well as northeasterly winds, while during the summer we have more stable wind is from the southwest, and is a continuation of the Meltemia from the Aegean Sea. With the currents, this is the currents and the sea surface temperature, because the oil spills, they need the sea surface temperature. This is the area here, as you can see, is an open area. It's not a close coastal area, and it's affected, of course. Oh my God, I have to go back. Okay. It is affected by the open circulation. As for example, you can see here is the Cyprus anticyclonic eddy. This is along the coast of Israel and Lebanon. But in our area, it was able to simulate and produce along the coastal currents. So it is evidently that we have currents along to the coast, eastward or westward. So this is important for the oil spill predictions. Then, of course, the first scenario, as I said, is a coalition of 2 vessels in this location, the location 2 for winter. Due to the prevalent wind, the variability of the wind, it is obviously from these superimposes of the sea surface oil spill concentration that the spill it is extended. This is the impacted, the permanent impacted oil on the coast, that it is covered mostly the whole basin, the whole Limassol Bay. With more, of course, concentration within and without and outside of the Limassol port. Of course, for each of these simulations, we have the fate parameters and so on, but this is not time to do it here. This is the same location, same parameters, but for the summer period, you can see here that because we have more stable southwesterly winds, the spill, they are concentrated closest to the port and mostly affected the touristic area, as for example, the Royal Apollonia. If someone maybe who have visited this Royal Apollonia, we had one of the MFSPP meetings there many years ago, as well as a coastal park in the area. Then, of course, you have for the third scenario, it was a coalition again inside the port. It was some repair. They said that some repairs there. So in this case, in the winters, as you can see, the superimposition of the oil spill, it was directed the concentration far away. And indeed, from the impacted the beach of the oil, as you can see, yes, they impacted the large extent of the coastline here, but high concentration inside the port. And different situation is we obtained it for the summer months, where again the spill it was concentrated close to the important touristic areas, again in these high stars hotels as well as the coastal park. And then we have the fourth scenario. This is a little far away, and this is the scenario with the transfer of fuel from one ship to another. Again, this is winter. In this case, it is directed away. And in this case, it's affected other coastal areas here and marinas here and beaches. While in summer period, again, the spill, it is more closest to the high star hotels. One of the things we found out during this simulation that 48 to 50% of the marine diesel, it is evaporated within the first 24 hours. And in addition, in most of the scenarios, even in some cases that it is located in the entrance of the port, in order to, the first impact on the coast, it was, we found out it was simulated after 24 hours. This is important to the response agencies in order to react in time and do this, the combating measurements. So next to this, as I mentioned from one of the beginning of my slides, that the area it is characterized by several wave breakers. And why? So in a frame of a different project, we requested from the combating agency in Cyprus to do some experiments to deploy virtual booms and to identify how much oil they will capture if they deploy them before the spill will reach the coastal area. So this is an applications with different time. I mean, all this scenario, we have followed the instruction from the combating agency. They just calculate the time they need to go from the nearest port to the locations to deploy and so on. We already published also this one, and this is response measure, the visual response measures. In the first top is without any measurements, so you can see here, this is the phase parameters and, with the oil on the sea surface, the red one, while the green one and the black one shows the oil that is permanent, the black one stuck on the coast, while the green one is available that may be returned back to the sea. In case we deploy 2 oil booms in the way of the dispersion of the oil, within 12 hours, you can see that the curve of the oil on the surface is reduces, as well as reduces the oil that it is stuck on the coast. And of course, here is an addition tip. In the case that the response agencies, they will use in the open sea dispersion within these 12 hours of window, then as you can see, the minimum of the oil will be impacted on the coast. So in this project related to this license for the Port Authority, it is evidently that these wave breakers, they serve at the end of the day as artificial booms. So from my point of view and from the point of view of the ecological people, everybody, they don't like these wave breakers because optically, visually, is a pollution to the eyes. They have constructed and deployed these wave breakers in order to protect the area from the coastal erosion. But at the end of the day, these they serve, as you can see, this is an example, that they managed to capture the majority of the oil spill in case of a real scenario. So some conclusion that I just summarize here. So that, okay, I don't want to go through, but I think that it was first we documented for the very coastal area that the downscaled data from Copernicus through Psychophos is able to do this simulation at the very coastal area. And in addition, first we have implemented as example, I mean, the oil spills in a case of fuel transfer from ship to ships. And of course, that indeed, okay, the wave breakers is considered nowadays is not good to do, should be below the sea surface, but nevertheless, they can serve as artificial booms. I think this is what I want to present today, and any questions? Thank you.
Thank you very much. Please, questions? Questions from audience? Please, Igor.
Yes.
Georgios, beautiful presentation. And I have a question. I think you made deterministic oil spills for that study, right?
Yes.
Is it worth doing probabilistic assessment too? So performing, I don't know, a number of simulations to check how they could differ, or in that case was not applicable?
No, in that case, as I said, we have run scenarios for 2 years. So at least we had, say, for each of the simulation, 2 simulation for the same location, same period. I mean, it was not able to do more runs, okay, because it was a time limitation allocated to us as well as the budget. But nevertheless, the port authorities and the response agencies, because after the end of the project, we have presented them the results, and they were very satisfied because indeed periodically they have some small incidents, and the citizens, they complain, and they complain the port. So in this case, they are also managed through this simulation, the report we have produced, that okay, the port is responsible in this case of an accident, but if some ship or coalition will be outside, this is responsible of the ship. So this was important.
Thank you.
Thank you, Dr. Georgios, it was excellent, this presentation. Just a question, a clarification. The booms are constantly placed there and you consider their effect? Or it is supposed that you have enough time from the creation of the oil spill to go and put them there and have in advance somehow determine where and the way you install them?
You mean the wave breakers, you mean?
No, the booms. The
booms. No, there it was no constant. It's just the response agencies, they said that... I mean,
you have time to do that?
Time, yes.
You have time? You have to start on the...
Yes.
On the click.
Yes. So the response agencies, they tell, okay, if we have a case here, I need a certain time to mobilize the people, the ship, to go there and deploy. So based on this information, initially we run the model with no any measures, and then we know where the spill will go, and then in accord to the timing they gave to us, it was the deployment. They said also the deployment depends on the...
Thank you very much for your attention. Okay. It's time to lunch.
Excellent work.
Thank you, Nikos. This is the time to go to lunch. Otherwise, Vanessa kill me. So, folks, I'm here on behalf of Marina Sanz Martin, who is a postdoctoral researcher at Spanish Institute of Oceanography, and she tried to reach us from the United States. She saved PowerPoint presentation with sound, but unfortunately we could not, get all the skills of this presentation, so I will read the text which she is provided, and I believe that our society is very supportive and help me if I'm not right, especially in biology. So today Marina wants to deliver the speech about climate change and how climate change is driven species redistribution in the Western Mediterranean Sea. There are three research questions. First, are Mediterranean demersal species escaping in the threat of climate change? Second one, which is the role of climate velocity and the thermal and depth preferences of the species? And third, is there a meridionization process in the Mediterranean Sea as previous studies report? Species redistribution and fishery stocks. As you can see, there are important shifts in marine socio-ecological system. People found profound alteration in ecosystem structure and function and changing fisheries. And there is a question, of course, about impacting on human community. Next slide about climate velocity in the Mediterranean Sea. And this explanation of term meridionalization. This means increase in the abundance of native fauna with southern species. Am I right? Then, how does it work? From northeastern Atlantic, signals goes to community that like warmer temperature and expanded the area, expanded at 250 kilometer per year. It's not area, it's a flux. While cold communities have retracted at lower speed. Oh, you understand the idea that behavior of biota depends on type of species. And on the left, you see contemporary classification of the climate velocity trajectories. Maybe if there are questions, climate people will help me. And on the right, future climate velocity. Next slide about, again, this not very simple to me climate velocity in units kilometer per year or kilometer per decades. And climate velocity is characterized by the speed and direction of islands migration. Islands can be based on the sea temperature in case of terrestrial climate velocity, temperature and precipitation isoline, travel across the seascape due to climate change. If you catch, I will be very, thankful. Climate velocity is a metric of species distribution movement. It's defined as the speed and direction at which species must migrate to follow thermal isolines migration to maintain constant climate condition under climate. So, as I understand, this connected with the adaptation of species to climate change, to change of temperature. So if some species love and prefer warm water, they will track warm water. If they prefer cold water, they follow cold. It's my interpretation. Next, spatial gradients we're calculating using a 3 × 3 neighbor cells. So the basin is divided to cells, and there is evaluation of spatial gradients using 3 to 3 neighbor cells. And there is a, how to say, special definition of these cells. It looks like, in my opinion, like Sutherland interpolation in our cases. So it's kind of, this is a mesh introduced on the Mediterranean Sea, and using this mesh, the data was interpolated according to 3 to 3 rule. Next one. In this map, we can observe the climate velocity in kilometer per year with some hot spots in southern of Balearic Islands and offshore Valencia. Next. Marina has combined climate velocity with a long-term database on demersal species up to 102 species for 25 years in the some model, which is a fisheries management unit where there is international bottom trawl survey, some Mediterranean program, samples every year in the late spring and early summer. Using this density of each species, Marina calculated the center of gravity of this population, which is the mean geographic location, and she traced climate change variability by means of this center of gravity. Next slide is about shifts in demersal species. Demersal species of the fish which live near the bottom. Significant shift is centered on gravity. So I'm sorry, I could not. Okay, she found significant shift in this center of gravity, which describe 40% of species. And she detected south and southwestern general shifts, south and southwestern general shifts of these populations. So demersal fish, it's my interpretation, feels temperature and response is shifting to deeper water. No? I'm sorry. So feeling this high temperature goes to the deeper water. But I don't understand why, but maybe I'm wrong. Maybe they prefer to go to shallow water, maybe. And on the bottom you can see species which are studied by Marina. Next. Here, Marina analyzed the temperature and depth preference of species according to main temperature and main depth in x-axis and the range in y-axis. Over the x you see mean temperature, over the y you see rank rank temperature. And T1 and T3 are connected with cold water species, and the T4 is connected with the warm water species. So, as you can see here, the shift between centers of gravity in the last 25 years increases with increasing climate velocity for all the temperature preferences. Then you see the same. And without comments, we will try to understand. So we see the connection of velocity, climate velocity, with the shift. Again, units. I could not understand units because climate velocity in kilometer per year, okay, but shift of species, maybe shift in position of gravity center. So inertia and dispersion index, as I understand from literature, do not show a clear response to climate velocity, but a significant difference for the deep water species. Conclusion. Climate velocity presents hotspots south of the Balearic Islands and offshore Valencia. Displacing towards south and west block northward expansion, and this is connected with the meridianization paradigm. Increases the evidence of species distribution shifts following local patterns of warming. Species such Galeus metastomus, Physis blendosis, and Lophius budegassa are going toward deeper water, but this capacity in the future can be exhausted, and other studies reported in the Northern Ocean. Since all the species with different thermal preferences are shifting their distribution, it can indicate a resilient mechanism to cope with high velocity of climate change, as I understand. So, and fortunately, if you want to deep in details, please study this publication. Fortunately, everything is published. Thank you very much. So, next speaker, please. Manuel Ruiz Villarreal, please. From this institution. I don't know how to go to, no. Please help to go back to normal mode.
¿Tu nombre?
Ruiz Villarreal. Es un PDF.
Vale.
Es un PDF.
Vale. O sea, sí.
Ese.
Vale, te tengo que poner la pantalla un segundito.
Vale.
Listo. Te lo pones en...
¿Y qué es F? ¿Te lo pones en pantalla? ¿Te lo pongo en pantalla completa?
Sí. Ah, ese es el botón. Si no, ¿cuál es?
F5, ¿no?
F5, sí. Bueno. Okay, good afternoon. So I work for the Spanish Institute of Oceanography, but in the Oceanographic Center of Coruña. It's not the Mediterranean, it's the Atlantic. But I'm very happy to have been invited to give a presentation on our developments of the Ibirus community on coastal risks. And it was a great opportunity to know your vivid community and to know that you are talking about applications and about science. So I'm happy to have been here listening to the presentations. And I think you already know that Ibirus is the rus of Eurogoose in the Atlantic area, and we cover the Atlantic facade, the economic exclusive zones of Portugal, Spain, France, Ireland, and the UK, and including, we don't have it in this picture, including the Atlantic islands, the Canary Islands, Azores, and Madeira. And I wanted to tell you about the developments we have done during an Interreg area Atlantic project that just finished last year with some extensions because of COVID and because of capitalizations calls. So, no. Okay. So this slide is the work plan, but it's not for you to have a look at it. It's just that is a typical operational oceanography project where we have an effort on the coastal observing system, on downscaling the models, and I want you to have a look at there's a lot of modeling configurations in the area, and we wanted to work together and to do joint development of coastal risk tools in different areas, coastal flooding, pollution, search and rescue, oil spill, and the main focus was to do it with the standard available observing and processing strategies to have the tools to be transferable between different areas and different countries. So that was the process we followed. So at the beginning, we review the 16 tools for different coastal risks. So every partner, and we have been working together for several years, the community, we knew each other. So some have some nice applications for search and rescue, for giving information to shellfish harvesters, to coastal risks in harbors, to support aquaculture operations. So we put together all this previous background, and then we selected some MyCoast tools for the different risks based on the existing tools and which ones could be more easily advanced and developed to be used by all partners. And one important thing we did during the project was dataset harmonization, and I want to concentrate on numerical models. So we went on with a standardization of numerical models. Over the years, we have been able to disseminate our model results from all model configurations in the area in a way that can be used by the different tools and for different applications. And so we focused on the standards, on interoperability, and we wanted to do joint development, so the code was shared, and we even have an Ibirus repository, software repository, and you can have a look there. that some of the code we developed is available there. And then we did some pilot demonstration along the Atlantic area with that idea that we want to demonstrate that these tools can be used easily in different areas. So the first tool, and we have seen some nice tools in this meeting, was a tool aiming at forecasting extreme events and providing flood risk warnings for municipalities. So what we did, and our partner Meteo Galicia, with the help of others, they developed a suite of plugins and Python code for QGIS, so we could ingest metocean data to forecast whether or not historical flooding thresholds will be exceeded. So in QGIS, you could introduce the information about flooding levels. And during the project, we were able to demonstrate it in different towns along the Atlantic area, in Coruña and Vigo, in Galicia, Bilbao in the Basque Country, Galway in Ireland, and Lisbon. So these Interreg projects are about indicators, so we could show off and say that we supported a population around 1.5 million people. Other area of where we were developing tools was search and rescue. So the Marine Institute had a tool called Adrift to facilitate the use of the Lagrangian dispersion model ICTIOP, and during my course, we were able to implement, instead of ICTIOP, OpenDrift, and as you can see, OpenDrift has more information about windage and the effect of wind on transport, and here you can see some nice example on Galway Bay, that it was a paddle surfer that disappeared in Galway Bay, and the good thing with this windage is that depending on the properties of the object, you can simulate the cross effect of winds and currents on the dispersion. So then it was prepared to be run to use OpenDrift, this Adrift, and we were able to use it with different models, ROMS, NEMO, and FBCOM. What is the idea of this Adrift interface is to be able to have an easy and user-friendly, because they were tackling as a main user the Irish Coast Guard, to be able to launch simulations for quick response of search and rescue, for example, these paddle surfers or some people that fall at sea. So it's ready, and it was some interaction with the Irish Coast Guard, and they are using in some of their operations, especially in the Dublin area. So another tool, and Francisco already mentioned that there's a 3D model with configurations all along the Atlantic area, the model MOID. So there was an effort to code a plugin or a Lagrangian interface to launch particles with MOID and in a QGIS interface, so that it can be used to support pollution contingency plans. And in fact, this is used in the pollution contingency plan of Galicia. And here you have an illustration of the use in one of the Galician RIAs, in Ria de Arousa, and also in Plymouth Sound in Devon, UK. So it has been coupled not only to MOID, but also to ROMS and other models. Other interesting tool that we decided to develop was tools based on Lagrangian coherent structures, because if you are able to compute in an easy and robust way the spatial distribution and the time evolution of finite Lyapunov exponents, it's a good way of diagnosing dispersion and retention areas, and also you can estimate the concentrations and resident times of pollutants, and here this is an example in Plymouth Sound in the UK, in England, and also in the Rías de Pontevedra and Vigo. And this is very interesting for pollution exercises because you can identify hotspots where marine litter and pollution may accumulate, and we were able to support different users. For example, in Plymouth, they were supporting, giving information for users bathing or swimming at sea. So other application where we knew there was an interest of having a tool is called Weather Window. So in a previous Horizon 2020 project focused on aquaculture, we realized that it's useful to have a forecast, to show forecasts of wind and wave data to help aquaculture operators or even the wind renewable energy operations in this kind of viewer, so that they can see when is the favorable window for these operations to take place. So if wind conditions and wave conditions are better, and you can provide a forecast, it's easier for them to plan their operation. So the good example apart of this tool is that we were able to implement this tool in 50 sites, including the sites like aquaculture sites. So we were able to show results on mussel harvesting areas in Ireland, in Galicia, and in the Basque Country. Also, we were forecasting, or we implemented this weather window in places where we had oceanographic buoys, in the Western Channel by PML, and in Santander, our institute, IO, and in the buoys of the Xunta de Galicia, and also in some pilot sites where they are experimenting pilot renewable energy platforms in the Basque Country, in Portugal and Galicia, and using different wave models. The lower resolution Copernicus configuration that allows us to cover the whole Atlantic area, but also SWAM very high resolution configurations, like for example in Galicia, in a resolution of tenths of meters. So also we were interested in this transnational component of cooperation. So as you know, every country or member state, they are doing pollution exercises, but national pollution exercises, and sometimes they are together with transboundary partners. And in this case, we applied our tools to a marine pollution exercise in the border between Galicia and Portugal. And there were some, you know, these exercises that it's an emergency experience, and they launch drifters, and they make sure that all ships and all mediums are deployed in a smart way, and they are able to prevent the pollution to find the coast. So we were able to show the different tools there, and as I told you before, this Moid Lagrangian is integrant part of the Galician viewer for pollution exercises. So we were able to show that we can support in a transboundary different countries with these tools. So this is the last slide to show that we were able to develop together, to do a joint development of tools for tackling different coastal risks using standard models. And as you can see there, for every coastal risk, we were able to use different models and accordingly different model configurations, because ROMS and FBCOM and MOID, in different areas we have configurations of that model. So we were able to cover with these tools different risks, but also the whole Atlantic area, because we did a big effort on standardization of the model output, but also on standardization of the tools so that they were able to ingest model output from different models. So this is the last slide. The main aim of the project was to have a long-term effect, and these Interreg cooperation projects are very concerned about capitalization. So we were able to show that what is the basis of operational oceanography, a cooperative effort in which ocean observing systems, together with modeling, can support end users in the marine sector. So this is not the only project we have been able to show this. So we have different projects where, for example, we developed early warning for harmful algal blooms in other projects, and we have some prototypes to give information to aquaculture industry to support their operation. And it's very important, we did it through joint development, so we were sharing the code, we were using and introducing improvements in the code, and not only in the code for simulation, also for ingesting different model output. And finally, I think we were able to demonstrate that these tools are relocatable and can be used all along the Atlantic area. And we did some presentations to users and workshops, and now some of the tools are beginning to be used by the Coast Guards and pollution managers and so on. So thank you very much.
Hi, thanks for the presentation, really awesome. And I was wondering, as you're going through the use cases, I love QGIS, I love the plots that you can make with that. But at the same time, I never thought about the interface in QGIS, so that's very interesting. So about these projects where you have that interface, do you have some sort of training for the users and how to interact, or that is, how is the usage of the tool at the end?
Yeah, you know, users are very diverse. So for example, for the flat tool, we have some tutorials, but that was for advanced users, because not every final user is able to use QGIS and is not able to gather meteor ocean model output and get the coastline and the elevations. So there, for example, for that flat tool, there's a tutorial. And also we did some demonstrations and tutorial of these, for example, adrift tools and the other tools that are closer or easier to use for the final user. So you can have a look at the project, and the information is there, the code is there, and there are some tutorials. I will make sure that the links are working.
Thank you.
classified according to its individual behavior. For example, some pollutants tend to evaporate very quickly. They call evaporators. Some pollutants tend to float at the sea surface. They call floaters. Some pollutants like to swim immediately to the bottom. They are called sinkers. And according to the individual behavior, there are special codes which allow modeling this in uniform way. And I saw that Mahit did it. I've never seen it because I know only one expert in this area. He's Sebastian Legrand from Belgium. He is the only well-known developer of HNS, and I see that Mahit also works with this. Do you know, Francisco or Manuel, which kind of hazardous and noxious substance are modeled from this project?
Okay. Now, this project, the main effort was in showing this joint development and these relocatable tools. But there have been some projects of some of our IBRUS partners with Sebastian Legrand, where they have been working on HNS and some Interreg Europe projects. And,
If you have this model, please publish, because we need to understand. Thank you very much. Thank you.
Okay.
Please, yes.
Just one question. I see from the list of models, on the list of models, you, I think, contains both structure and structure hydrodynamic code. So the suite works well with both.
with some of them. You know, it's a matter of having a good interpolator taking into account the original grid. So I'm not showing it. Yes, you know the Lagrangian, you have to interpolate to get the winds and the currents in the position of the. So we, for example, with FVCOM, we were able to for all tools to use FVCOM, that is unstructured. So it's a matter of writing an interface to FVCOM.
Thank you, Manuel.
Okay.
Please, next speaker.
Your comment about the HNS, yes. So the model Lagrangian has an HNS module that was developed and applied in other projects, like he was mentioning, like Manuel was mentioning. It's a bit difficult to validate because you don't have so many accidents with the amount of data that you have with oil spills. But there were some projects from the how it's called, the Agency for Protection Agency for the European Union, like Mariner. There are several projects where this was tested and validated, and the code is all open source, so you can have a look at it.
Thank you very much. I wish you less data for validation. So next presenter, please, Carlo Brandini. He is an expert in modeling from a very famous group, CNR ISMAR and Consortium Lama. Please, Carlo.
Thank you, Svetlana, for the very famous one. I don't feel like that. I take the opportunity of the nice title of the workshop this year, that is boosting the understanding of the climate adaptation for the adaptation of the Mediterranean area, essentially. So I think this is quite on the focus of the workshop itself. As we see also in the first lecture of the workshop given by Gian Maria Sannino, there is a big attention on the coastal areas because they are themselves hotspot for climate change. We know that there are some processes acting at different timescales. One is sea level rise, the other is coastal erosion, the other are short-term effects like storm surge. All these processes interact together, so there's not just one model that can do all this job. No, there are several different models that better describe single aspects of all these interacting phenomena. That's why the SCORE project, that is a European Union funded project aiming to increase climate resilience in European coastal cities, is looking for integrated solution based on smart technology and nature-based solution. There are 10 coastal cities that are involved in the project, both in the Atlantic area and the Baltic Sea, like Gdansk, or in the Mediterranean area itself. For instance, in the Mediterranean, we have Villanova, that is close to Barcelona, Massa in Italy, Tuscany, Benidorm in Spain, Samsun in Turkey, that is on the Black Sea. So to increase the participation of coastal communities, stakeholders in the project is organized at a local level through the so-called living labs that are active participation of citizens, stakeholders, scientific communities to this kind of common initiatives through which there is a sort of co-design of adaptation solution. For instance, we produce inside the project an EBA catalog that is contain a number of possible solutions for the floodable park to green roof to several different, of course, even on the marine side, both on the land side and the marine side. But finally, to better design all of this, we have to cope with an extreme, a big jump, no, among the scale of the climate services which provide the needed data, so the global data we need, through which the typical scale is the order of 1,000 kilometers, and the typical small scale element is the so-called model resolution, that is one of the so-called eddy resolving models, so is the order of 10 kilometers, for instance. While at the local scale, we need completely different data. We need data at the order of a few meters, because we have to describe the behavior of a flood with respect to a single building, because every single building has a different value, every single part of urban districts. So this is the scale of urban hydraulics. It is a different job. So, but to jump between these two scales, there is a huge downscaling work to be done. And this is done by different models. For instance, hydrology is very important to describe because there is a big interaction between the scale of urban hydrology, and in this case, we implement specific hydrological model in the project, in specific coastal cities. Then the sea level model that is part of this, normally described by hydrodynamic models, but hydrodynamics is very complicated, so we use physics reduced sea level models. In this case, I will show you. Then wave models are very important because waves are important, they impact on the coast. Then there is a huge activity on extreme value analysis because we need the design values for developed scenarios that then can be run using hydraulic models at the urban scale to finally produce hazard maps on different hazards. Downscaling wave climate was probably the most big effort the biggest effort we did in the project, because there are no available products at the European level still available through the Copernicus services at the right time scales, because for instance there are some products available but not. We need models that can be useful at the urban scales, that mean at a few hundred meters of resolution. So a structured grid modeling is the right tool to do that. So in this case, this WW3 implementation, in which there is a big representation of from the Atlantic to the European coastal areas. Forcing is done by different implementation of Aladdin inside the CM IP5. Then the scale in sea level was performed through the implementation, in this case, through adaptive grid implementation of SciFem, using the same forcing. I will explain later why it is important to use the same grid forcing, but because essentially we are also interested to compound phenomena, so it's important to have a common forcing phenomena for all this model, including the hydrological one. Then the hydrological dust scaling that is performed through the List flood, that is the official model by the European Community, developed at JRC. So all this model, of course, required a big effort in the model implementation. And finally, even a huge effort in model calibration, because we need the local data, for instance, river discharges, river level data on the river. We throw river gauges to fundamentally calibrate the model, so a fundamental hydrological simulation. So finally, this is the scale we are interested to, so the scale of urban flood modeling. In this case, all the downscaling models give boundary condition to this local scale model. This is the scale of, normally these models are performed by civil engineering or environmental engineers, because this is the scale at which we can design solutions. For instance, we implement ecosystem-based approach at this scale, no? So this means, for instance, the change of infiltration rates in different parts of the city, the change of morphological features. This means the most difficult part is not the hydrological one, but is to make the sea level data and waves to speak with the rest. So there are different approaches for it. One more simplified approach is based on using parametrization, for instance, for wave run-up and setup. Wave run-up is very important, like wave setup is performed through SciFem, and all the sea level, the wave run-up can only be described by phase resolving models. That is a part through which we are right now working, using models like FunWave or X-Beach that we also saw this morning in the presentation of the colleague, to capture detail wave dynamics and their impact on coastal areas, also taking into account of very coastal waves, interaction between the waves and some coastal features, including human-made protection for the land. So finally, taking into account the 3 different coastal cities, what we see performing all the simulation for different scenarios, in this case RCP 45, RCP 85, in both the historical and also considering different period, by taking the same return period, in this case 50 years, we see that, for instance, there is a constant increase of river discharge, and this is due to the extreme value that we know are going to of rainfall that we are going to increase. Although the cumulative precipitation is going to decrease, the extreme values are going to increase, while the combination of sea surface height, so the sea level, plus the run-up that is given, is a strong contribution from significant wave height in the breaking breaking area, is not expected to increase by itself, because I agree with the presentation given this morning that there is no specific trend in significant wave height in Europe, at least in Europe, but not something. There are other phenomena of interest, for instance, that are variation in wave direction more than in wave height, that should be taken into consideration. These are the results for Massa from what concerns some flooded area extension. For instance, on the top we see the results of the historical run, so using the historical part of the wave projection, the climate projection, in which we see, for instance, for Massa, that is considering 50 years return period, there are areas that are affected by riverine floods and not by coastal floods even today. This is not exactly the case, because, for instance, last year we have a big flood in Tuscany. Maybe someone of you remember at Campi Bisenzio, there was a big flood in Tuscany. In this case, there were also in the coast, even in the first slide, there was some picture of the coastal flood happening in Massa. But what will happen in the future is that although there is not an increase of wave activities, the level of, for instance, consider the RCP85 scenario of the year between 2045 2095, the extension of coastal flood is of the same order of magnitude of the extension of riverine flood. This is a major result, because it means that what today is not a problem, so the coastal flood, it will be in the future, and it's because the sea level rise will be the major driver of this phenomenon. This is the only difference, is the sea level rise that produces this. Inside the project there are several tools that were available for estimating the economical losses. For instance, there's a tool dedicated to financial resilience, and as I told you, there is a constant dialogue, discussion between this coastal cities living lab and the scientific technological part of the project to design together ecosystem-based solution, in this case for the Villanova area, in which we see what is the difference with and without the implementation of ecosystem-based solution. In this case, these are intervention on the river stream. Compound phenomena are very important. It will be a huge topic to be discussed. Yet the compound of hydrological component with the marine are very complicated because normally the compound effects can be estimated by using specific copulas function, so specific extreme distribution. This is not the case. Our idea is to select some specific case using some tool like the weather type classification, because we know that there are some weather types that brings together storm surge and rainfall. So these are the events to which could be of interest in selecting specific compound events. Otherwise, from a simple statistical processing of the value from historical time series produced by using projection models would be very complicated. Finally, there is also some modeling components dedicated to estimating the long-term morphological evolution using, in this case, specific morphological that will be, even in this case, very interesting to estimate the compound effects with future storm surge. These are the conclusions, but I think I spent most of my time, so thank you for attention.
Have you already started to sell building insurance?
The economic maps I show are dedicated to financial resilience, so to estimate will be the amount of insurance that should be applied to this case.
Yeah, call us as partners.
Yeah.
Thank you. Please, Christian.
Thank you, Carlo. My question is about how you consider sea level rise in your modeling.
It's only at a local level. Okay. So by adding the sea level using the projection from the CMIP5, so what is available. So in this case, the maps I showed will something around 60 centimeters for the last decades of the century.
Are you also evaluating how the uncertainty in the prediction of sea level or rainfall impacts on the economic sector?
Yes, but only, this is a big problem of this simulation that were very time-consuming and computational consuming. So the best would be to have ensemble simulation. This is not our case. So only through the confidence intervals inside the cumulative distribution, this is taking into account this. Yes, taking into account the interval, the confidence interval, but that's all.
Very interesting presentation. I have a question. I'm here.
Sorry.
I have a question on your slides about adaptation. So you were able to simulate scenarios of a railway, of a change of land use from agriculture, but
not at the scale. I agree with you. There are there are some ecosystem-based solutions that should be designed at a level of the river basin, so at the hydrological basin. It will be the case. But in our case, we simply implement ecosystem-based approach on smaller areas. So only modifying normally morphological elements or the permeability of specific. So it's still a lot of work to be done.
Yeah, but you could even model the permeability of...
Yes, but for the hydraulic, for the last mile, not for the, what would be very effective would be the simulation at the river basin scale.
Yeah, very interesting.
Thank you, very interesting work, Carlo. About the last mile, let's say, of the riverine flooding. You mentioned, maybe I missed something, about compound events. So, for instance, the riverine flooding can be exacerbated by the combination with storm surges or whatever. For instance, the flooding that the maps of flooding, of riverine flooding that you show, were only considering one single event of riverine origin, or it was somehow compounded with storm surges, coastal storm surges?
The tools we implement is able to do both, because we take a boundary condition from the river's flow by taking water. But right now they are separated, because the full computation, as I told, of compound effects is very complicated. That's why I would like to introduce some other tools like weather type classification. Thank you.
Thank you, Carlo. Again, come to us more frequent. Yes, please, next speaker is Africa de la Morena. Yes, very good. Nice to meet you. Please. University of Málaga.
Hello, I'm Africa. I come from the University of Malaga, and I'm going to change a little bit the topic of my talk because I'm going to talk about an experimental approach. It's not that modeling or something like that. And I will divide my presentation in 5 parts, beginning with a little bit of the context of my work and the need of it. Well, you were talking about the climate change and all the consequences it has. And I'm going to talk about the changes in species distribution and specifically in the creation of or development of invasive species in different environments. In the marine ecosystems, we can think about different cases of invasive species, such as the blue crab or the lionfish, but I am going to talk about the macroalgae. Okay, for those who doesn't know what it is, macroalgae are photosynthetic organisms really, really important for the ecosystems because they provide food and shelter for different species. Also, they are hatcheries for the babies of different economically interesting species, and they play a crucial role in primary production. However, with the changes of environments, and specifically with the climate change, global warming, and all the stuff, some of them can become really invasive because they are dispersed really easily from one place to another. Some of them are really easy to adapt to higher temperatures, for example, and so they can become competitive for other native macroalgae or other species, making changes in the environment. Some of the causes that create these invasive species are, as I said before, the climate change, but also the maritime traffic, as well as the trade of species. And talking about the maritime traffic, the Mediterranean Sea is a hotspot for marine biological invasions because we are connected with the Red Sea and with the Atlantic Ocean. Specifically here in the Alboran Sea, we have faced six marine invasions just of macroalgae in the 2 last centuries. But now we are facing the most important one, which is the Rugulopteryx ogamurae invasion. This algae is from Asia and it's brown. It has created unprecedented ecological, economical, and social impacts. For those who like the models, I included this map, which is the favorability of this species in the Mediterranean. As I said, it is from Asia, so it hasn't to be here. And with the global warming and the water temperature increasing, it is also watched in Galicia, which is really strange. And also it's, the current distribution is until Italy. So the problem with this species is that here in the Alboran Sea is the main threat to the marine biodiversity because it colonizes the rocky substrate, as you can see the photo, and it replaces native macroalgae and affects other species. And also not only ecological impacts, it has unprecedented economical and social impacts here in our coasts. First, in the fisheries, this species is entangled in the gears, in the fishing gears, so the fishermen cannot catch fish and they catch the algae. So it has decreased the level of fishing here in the last years. And also it affects the tourism because, as you can see, there is high biomass accumulated in the shore, and it affects people because they don't want to go to a dirty beach. So in this context, the Spanish government has published the first strategy of control for a marine organism, or animal or plant. Okay, this is the first one. So it's really, really important. And in this strategy, they identifies the traditional fisheries as the main affected sector, but also they identify them as part of the local dispersion of these species. So to avoid some of that impact, to mitigate that impact, this strategy proposed to develop some disinfection protocols to disinfect the fishing gears affected with Rugulopteryx ogamurae. So before they are used in places not infected with this algae, they can avoid the spread of these species. So in this context, I am going to show you the objectives of our work, which are to identify the different chemical products and physical stress that create that can inhibit the photosynthetic activity of this algae, and also to determine which treatment could disinfect fishing gears. So, well, in controlled conditions, which is in harbors or something like that, not putting chemical products in the sea, of course. So we can control and mitigate the impacts. How we did it? So we took some biological samples and we exposed them to different chemical products and physical stress. Then we measured the photosynthetic activity of this plant, and then we put it in seawater to see if it's recovered or not after that stress. Which treatment did we use? Well, chemical products are acetic acid, copper sulfate, bleach, and other ones. And physical stress, we expose them to high temperature and to high light, so we can model a little bit the water temperature increasing. Also, we shock them in the osmotic way using fresh water. And the photosynthetic parameters we measured were the yield of the photosystem 2 and the FVFM, doesn't matter. So we can calculate the inhibition percentage comparing the treated algae and the control algae, which were algae in seawater. So the results we obtained, first, exposing them to acetic acid at 4 and 10%, which are around the household vinegar concentration. We can see that after 10 minutes of exposure, it is at least 90% inhibited. Then we can conclude that this product is effective, and also it's not toxic because we use it in our salads. And then inhibition is permanent after 24 hours in seawater because the inhibition doesn't increase after that time. So we can conclude that it's good. So another one was the copper sulfate, and then we can see that the higher times are not better for the inhibition. I mean, only short exposure times and higher concentrations reaches high inhibition. So we can doubt about its effectiveness. And also we can see that the photosynthetic activity is recovered after putting the algae in seawater. So we can conclude a little bit that this species is kind of compatible with the copper sulfate. And then talking about the physical stresses, we put them in fresh water, which is strange for marine organisms. But we can see that it's not sufficiently inhibited, at least before 24 hours. So we have to wait like a day to have high inhibition percentages. So we can conclude it's not effective. And it's really strange because it's a marine organism, but it can survive in fresh water. We don't know. And then, well, the inhibition is maintained over time. That's matter. And then we put these plants in high lights, in really high lights, 1,600 of micromole, in 3 temperatures. And we see that in higher temperatures, the inhibition after the exposure phase is recovered. I mean, the inhibition is decreased. So we can see that this species is resilient in higher temperatures. In higher temperatures more than in 15 grades. So this is not the first time people used chemical and physical products for invasive species. It's used around the world. For example, with Caulerpa taxifolia, they used bleach and copper sulfate, which they did directly on the seawater, which is in the sea environment, so it's not so ethical. But they concluded that the chemical products are more recommended than the physical ones because of the effectiveness. And then the main conclusions we had is that chemical products are better, physical stress is less effective and more expensive, and the acetic acid for us is the best solution for the fishing gears. And the next steps is to scale up the experiments to use them in the harbors, so we can disinfect the fishing gears after being used in infected places and before they are used in healthy environments. So, well, that's it. Thank you.
Thank you, Africa. I feel that I've choose wrong subject. Please, your question, audience.
There.
Is there any commercial use for this algae? I mean,
Well, here in Spain we have a really intense debate with that. I think it's been used for sauces and also to do some toppers. And I don't know, there are some uses, but they are in experimental phases. I mean, there is not a commercial use for now, like the blue crab that you can eat it directly. No, it's not the same. We don't have a commercial use now.
Please, Francesco. No? Okay. Okay. Just.
Sorry, that was a nice presentation. I was wondering, do you know how quickly does this spread?
Yeah, the first time it was observed here in Cádiz, in the Strait of Gibraltar. It was in 2016. So in just 3-4 years, it has been spread to all the north coast of the Alboran Sea. And now, after, I think it's like 6 years, it's already in Italy. I mean, it's been observed in Sicily, so it spreads really, really fast.
So how many people and how much acid will you need to extract this?
A lot, but no. The objective of this work is not to eradicate the species. I mean, it's impossible, but it's to mitigate the impact in the fishing years, so we can avoid the spread of these species in the few places that are not infected already.
Thank you.
Please, next question. Yes.
Yeah, thank you for your presentation. That is my question, because for mitigate or for eradicate this microalgae in the natural situation, that will be very difficult with acid. We have the same problem with sargassum in Atlantic, and they try many things to eradicate it, but in the natural situation, it's very difficult.
Yeah,
so use acid to do the eradication. I think that will be very difficult.
Yeah, it's really difficult. I mean, I think it's possible. It's just focused on the controlled conditions. I mean, it's not directly in the sea environment. For example, in the sargassum case, I think it would be impossible because it's a really high biomass that goes with the currents in the ocean. So it's like impossible to treat the species there. So.
But they have something we can do to identify the origin of this algae. Well, for example, for sargassum, we know that they come from somewhere. So you can try to identify the origin.
Yeah, well, we know the origin of this species is Asia, the north, I don't know, the Japanese coasts. But there, this is a secondary species. I mean, it's not it's not really abundant there, but we think that it came with the ballast water of some vessels. So here, it found the conditions that makes them grow a lot. So here it's invasive, but there it's not. So.
Thank you very much,
Thank you.
Africa. So next speaker, please, Antonios Parasiris, Foundation for Research and Technology, Hellas, Institute of Applied and Computational Mathematics. Please, Antonios.
Yes, it's fine. Hello, everybody. My name is Antonis Parasiris from 4th. Thank you all for staying this late. I understand we're all tired, so I'll try to not to be a bit brief. My presentation concerns a 3D VAR study that was done in the atmospheric model WRF that helped us create an enhanced resolution digital twin of the ocean finally. And this work is being carried out in CMRL by me and Vasiliki Metheniti. That helps with the modeling aspects. And yes, so a little bit about digital twins and the motivation of behind ILIAD. As you already have heard today about digital twins, and I think you already know too much about it. The problem is that the ocean is a vast and complex place to model. So there are a lot of interactions, and the approach that we take is to have a lot of thematic applications for it. So others are based on different regions, and others are on different thematic applications. So some of them have data in them in some way, either validation, calibration, or assimilation in our case. And others use data to also do triggering alerts for some models or for authorities. An important part of this thematic splitting of the pilots is that we strive to be aligned with each other and be interoperable with each other. So we have many thematic applications, as you can see here in the site of ILIAD. There is the marketplace where you can find freely every application that's uploaded there. And the goal is to have every application Docker containerized somehow so that a user can download it and run it for her own region or application. So you can search by location there or by thematics. And you already know that the approach that we're taking for downscaling and enhanced model is for taking from global to regional and then to local scale resolution. So this particular presentation is about atmospheric enhancing the modeling because frankly we didn't have too many data within the region that we are interested in around Crete. So the digital twin of the ocean core modeling, as we call it, is based on the WRF-DA, which is already around the WRF to downscale to 3-kilometer resolution. And then we use data, atmospheric data collected throughout the island and the region to bring this closer to the reality. And we use then this atmospheric model to force WaveGauge 3 into 1-kilometer resolution and NEMO for hydrodynamics, again at 1-kilometer resolution. Where are the data coming from? The first step was to install some hydromasts, as they are called, in the port of Heraklion, which can measure currents in 3 different depths. And these will be used for our triggering mechanisms because we want the model to run the thematic application that we have to be also able to run when severe weather or current conditions are being met. The atmospheric data are from 3 sources. They are both from NOAA METAR data. They are from the buoys that fall within the O2. And we also have a network in Crete with meteorological stations, and we have maintained 2 of them, and they're kindly enough to give us access to use for the DA to see how better we can make the atmospheric model. As this is the main result for the atmospheric model. This is an ensemble of a lot of daily, 21 to be precise, simulations that it's forecast 3 days ahead. And we have this as a statistics with a mean error with the DA, which is the 3D VAR, the red one, and the blue is the control case, which is the WRF without any data assimilated into it. So we see a clear improvement, small albeit, in the range of 4 to 5%, and some forecast hours around 30 to 50. We see an even 7% improvement that we also find in the literature for other areas to be aligned with. So now going to the thematic applications that we have 2 pilots that we are responsible in the Cretan Sea. These are the general categories of pilots within ILIAD. The first thematic that I'm going to show you concerns optimal ship routing. The goal here is to minimize CO2 emissions, especially when we have severe weather conditions. We use, again, the forcing is on the left. We use the SIR2 software, which is created by CMCC. And here is an example. Even with this, this is an example of good weather conditions that we had. That was about 1% reduction in emissions. But in the paper of Manarini et al., they report much more CO2 savings in more severe conditions that we're going to test, and we're in the process of. Here is the visualization aspect of Iliad. Our pilots are visualized through GeoMachine, which is a UK partner, and they build these machines that everyone can make an account and see and access. Here you can see the two routes, and you can see that the currents are doing an anti-clockwise direction, so the ship is suggested to take the lower route to minimize CO2 and not the least distance one. This application also will enable the user to choose a date for the simulation date, and also in the future states to change the routes. Now you can do it within our domain of where we run the models, but this can be extended to take other input sources and be more versatile. If you zoom in now in the red box, you see the location of our station in Heraklion. This is the array of the hydromasts that I talked about earlier. And this outputs, each time that it finds currents above a current threshold, outputs an alert, and we take this alert and we run the model, the ship routing, and the future, another model that I'm going to show you later. And this is also plotted in the GeoMachine platform as an alert. This is the second thematic application that we have. It's the oil spill trajectory forecasting. As you have already heard from previous speakers, we also run the MedSlick2 software. Just we force it with our own DTO core models. And this is an example from the initial visualization platform that we had using a leaflet. And then we have, in the next slide, the GeoMachine version of that. So GeoMachine also can show in different hours and show the concentration of the spill and where it will be beached. It will be forecasted to be beached. The last thematic application that I'm going to discuss is a high-resolution 50-meter model for predicting waves that is also operational in our lab. And it concerns the port of Heraklion area. It also can be triggered by the adverse conditions that are detected by our sensors. And this is plotted in Adam platform, which is an Italian partner of ours within Iliad. And there the user can find also the DTO core models, all three of them. And also there is an API that supports this platform that you can freely access, and you can download all the data from there. And there are links to the marketplace as well, leading to both the Adam and the GeoMachine platforms, which is a place that brings everything together. The takeaway message is that we have tackled the problem of enhancing a model that concerns ocean and wave by taking atmospheric data and doing the data simulation on the forcing model, which is the atmospheric one. And then this can lead to thematic applications like we showed that support European Union goals for reducing CO2 emissions, managing marine pollution, and fostering sustainable maritime practices. Thank you.
Thank you, Antonius. Thank you very much. Very impressive presentation. Please, friends, questions?
Hi, Andonis. Thank you for the nice presentation. Just one question. which are the stakeholders that you are targeting for these two thematics applications?
Right. So for the oil spill, there are the people from the port authorities that want to be notified in advance, and also the Coast Guard. And then for the ship routing, there are companies that run the ships and that want to have greener practices. And also the service can be run on demand, and in the future release, we could you could go on demand and ask for your specific vessel. If you have a yacht or something and you want to take into account the currents, you can do that. This one is freely available right now for port authorities again, for safe disembarking and embarking of the ships when there are bad weather conditions. Yeah.
Thank you.
Thanks.
George, please.
Very quickly. So very interesting, the result of your project, Iliad. My question is about the atmospheric model you're using, the WRF, yes? The atmospheric model you are using.
The WRF.
Yes. So you use NCEP data or some other model to initiate?
I'm using GFS,
yes,
which is operationally, so it's forecast. It forecasts, we downloaded the 3 days forecast. That is in 27 kilometers resolution.
Yes.
And we downscale once into 9 kilometers and then to 3.
Did you, second question, did you try to compare with Skyron atmospheric forecasting system?
We didn't get the chance to. We have compared with the GFS, with its original model, and with in situ data, and we have a publication on that, on the comparison of how the atmospheric model, the downscaled one, performs better. And then this is a result that compares the DA version with the control case.
Okay, thank you.
Thanks.
Thank you. Okay, Nikos, please.
This is new in the lab. Yeah, it's open. Okay. So, but Yorgos, remember that very well that the initial version of Coastal Crete, the forcing terms were provided by the late Yorgos Kallos, Skiron, Skyron, and so on. And then on, we had another project with Yorgos before, where we also were structuring some civil protection models, and we were initializing Coastal Crete and the oil spill model with Skyron, because that was also the contract then. By now they want to play with different scales of grid, so that's why they are implementing their own model, so on.
To sum up our session, I'd like to tell you thank you very much to all people who works on, people who works on applications, people who ask questions because you inspire us to continue to work, people who do measurements because we know it's not easy to do this, people who perform modeling, because when we present our results to end users, we rely on you, on your work, on your job. Please continue. Thank you very much.
Please don't escape. So, I come here. This time I have my glasses, because so I can see what I wrote, because I cannot see anything. 6 years ago was better. It means that it's very demanding 6 years on MonGOOS. So, for the joking, I would like to, okay, I have to, yeah. So, as a first, I want to thank all the speakers for the wonderful, very important presentation, very interesting presentation that we have had in the last 2 days. And on this regards, I would like to ask you or tell you that your presentation will be converted in PDF, and then we will share to all the community. We will create a folder, and everybody can see the presentations and contact also the authors, so if they want to have another feedback. The second thing is that if someone doesn't want to, just please let us before. So maybe next week, because certainly we won't do it tomorrow, but as soon as possible, to just not deliver this. I want to thanks again, and I cannot, to the local organizers that I believe that it was a really beautiful 3 days, 4 days, 3 days, we had 4 days, but 3 days in a very beautiful location, and they really book nice weather, maybe too hot for us now, but it is so very nice. So thank you again for all the attentions and all the organizations. Also, I would like to thank the sponsors, all the institutions and sponsors for the catering, because you know that we are not, nobody pays to come for these meetings and to be member of MonGOOS. So the catering and dinner and everything is paid by the members. So in this context, I would like to thank Aquarius, that was yesterday, and then MonGOOS, CMCC, and of course EO again, and OGS. That I want to also thank you, but this is a special, and I would like to thank for the working group leaders, because during all this period has been very nice to work with them. I get emotional. And so they also for this workshop, it's not 1 month work. Comes from the beginning of the year, and it's a lot of work. So I would like to come here, Orenz, Manolo, Emanuela, Christians, and Svetlana. Here just to, for those who don't know, who are the working groups chairs. And because yeah, and because all the work that we're doing in MonGOOS is not really, we are meeting regularly, and there is a lot of work that each of the group is doing, contacting all the institutions that, you know, they reply very quickly to all our mails, and so thank you guys. I know this is on voluntary basis, yeah? So everybody is doing the work. It's not a project that we are not paid, and it's just everything is on a very voluntary basis. So thank you a lot, guys. And this, yeah, you just remain here because Alicia wants to take a picture of everybody. Let me see. Last but not least, I want to give the floor to Manolo for a moment. I want to say that there was a dissemination of this event, as you said, for the YouTube, in the YouTube channel from EO, so you can, if you miss one of the presentation or you want to get more in depth into this, okay.
Successful event. Thank you very much for working together for these years, and I cannot say anymore because it's just good words, and thank you very much.
Thank you very much. Ooh, I'm getting emotional. Very easy to cry. So just the last thing, this said YouTube. There will be, this is in Twitter. If you have Twitter, just go to Twitter to MonGOOS. It will be disseminating all this information and LinkedIn, and then it will be in Facebook from OGS if you want to see it. Okay. Just.
So just to finish the thanks.
We will take a picture. So just
Okay.
you are already here.
But from the point of view of the local organizers, I would like to say, first of all, thanks to several people. Maybe I will forget someone. One of them is to the technicians from Sonotest. Thank you very much. I know it's their work, but they have done always with a smile, always willing to help, and sometimes we've been 1 hour delay, no problem, they have been here. So we hope to count with you for the future, for other events. Thank you very much. I also express my gratitude to the catering. They are not here, to the waiters, because they also did a great job. It seems not so important, maybe science is the most important, but they make very pleasant this event. They're very important. Second part is when you see local organizers, you look at me in the face, a beautiful face, you see. Really, it's all our team from the Mediterranean Climate Change Group, Enrique, Cristina, Silvia, Araceli, Maria, and especially I would like to thank to Francina, the blonde girl over there, because I know all of you know how difficult it is to work with administration, all these papers, all these forms you have to fill. She did most of the work, and without her help, this would not be possible. So Vanessa already said, thank you to them that helped to organize everything, but in particular to Vanessa. Without Vanessa, I cannot understand MonGOOS. I don't know what will happen in the future, but obviously, when you say MonGOOS, you think of Vanessa. That's incredible work. And of course, thank to all of you, because not only because of the nice and the high-level presentations you made, but because you made our organization very easy. You have been very nice guest, and so it was a pleasure to host this meeting. And maybe you could think that after organizing this, especially those who has organized all the events, I am thinking I am fed up of this. I'm willing that you all go to your house, and I will not organize another meeting until I forget all of this. Yeah. But that's not the case. I mean that we are very proud. I think I talk on behalf of the direction of the Spanish Institute of Oceanography, or in particular of the Málaga Oceanographic Center. We are very proud to have hosted MonGOOS. You have seen that we have new installations, new facilities. I think they're very nice for organizing these kind of meetings. So I want you to know, as I said, I speak on behalf of our direction, that this is your house, and whenever you think you want to organize another event, whatever the kind of event here in our installations, you can count with us, and we will be very happy to have you here in our center and also in our city in Malaga. That I hope you have enjoyed your stay. Thank you to all of you very much, and see you soon.
You forgot, does anybody have some question, you know? So this is not a question, this is my remark. Me and Lydia, we were in Genova in 2018 when we elected Vanessa, so we get more what we thought that we'll get in these 6 years. Especially it was a very hard period. Each of us were also online, and it was very hard. So thank you for your work, and this was my comment, not question.
Thank you to your kind words, and very emotional, I would say. We want to take the last picture. Unfortunately, a lot of people have already gone, but we want to, if you, some come here up, and we just take the picture for the workshop. And with everybody, everybody. I cannot take this. ¿Me lo metes solamente?
In my opinion, there are too many Italians. No? What do you think about that? Huh? I think there's too much Italian.
For sure, next chair will not be Italian.
No. Emanuela, everybody wants you to be the chair.
We all decided we will vote Matthias.
Matthias?
The Slovenian.
Why not? I cannot, I'm not a member. But Matthias, yes, would be great. He will,
Bueno, ya cierra
he will be okay. Really?
It doesn't work, but we can all vote for it.
The young one can...
Yeah, we ask him. It doesn't know.
Alicia, bien.
Sí, claro.
Venga, venga, póngase para... Pero que se puede hacer eso.
Estamos como los bodyguards de Vanessa, ¿no? Mira.
¿De qué?
Yes, Manolo.
Aquí los dos malagueños.
Los reales.
We have to shrink? No.
Y gracias también por la invitación.
MonGOOS.
Alicia, we will move until you come.
Where is the next MonGOOS meeting?
And we know. Great. And just wait. I just want to thank a special thank to Alicia.
Yeah.
And have a safe trip home.